to address. Sometimes, in fact, your systems, our cells, make mistakes in trying to repair the damage. They try to create segments of the DNA. The DNA may break, the two segments may separate, and at that point, our cells guess a sequence. That can be bad news, because the sequence is a mutated sequence and survives mitosis. That means we have a cell that can reproduce itself, that can grow into a tumor, and we don't want that. We will see that there are radioactive materials. So there are materials that emit radiation, as well as machines that produce radiations, devices that produce radiation. And I'm sure you remember from high school times that there are some key types of radiations, and that some of them are stopped easily, some others not at all. So there are particles that we call alpha particles. We will see them again in a few minutes, that are very, very easy to stop. If we have time, I'll show you a detector that I brought with me. It's an imaging device. I also have a small source of alpha particles. It's all legitimate. It's a small Czech source, nothing to worry about. And I'll show you how we can see the tracks of these alpha particles, but if we put a sheet of paper, that'll stop them entirely. Another type of particles, beta particles, these are electrons. Now, by the way, I hope you know that when we say electrons, that doesn't necessarily mean negative electrons. Those should be called negatrons. So we have negatrons and positrons. They both carry a unit charge. In one case, it's negative. In the other case, it's positive. Alpha particles and beta particles are charged. Alpha particles are positively charged. Beta particles typically, but not always, negatively charged. As such, they do stop in matter after a certain range, a certain penetration depth. So first concept that is very important, charge radiation stops at some point on its path. But then we have neutral types of radiations, electromagnetic waves or packets of electromagnetic waves, or particles that are neutral. So these are gamma rays or X-rays. The denomination depends on how we make them or how they're produced. And then we have neutrons. Neutrons are constituents of nuclei, and they're neutral. As all neutral radiations, they're not stopped entirely in matter. They can be attenuated. And I'm sure you know that a good shield, it's common knowledge, that a good shield for photons is lead. You may not know that a good shield for neutrons is something that contains hydrogen. Concrete, for example, plastic, water. These are very, very good shields for neutrons. But all they do is attenuating the intensity of these radiations. They don't stop them entirely. Now, still from high school, we're taking it from the basics. You know that if you had a source that emits multiple types of radiation, for example, alpha particles, beta minus, negative electrons, and gamma rays, and if you were to put it in front of a magnetic field, you'd see a different deflection of alphas and betas, and you'd see gamma rays going straight through the magnetic field. Gammas don't carry a charge. They're not affected by the magnetic field, whereas alpha particles being positive will deflect in one direction and negatrons, beta minus particles in the other direction. If they had the same energy, alphas and betas, the extent of their deflection would not be the same because their mass is different. So these are concepts that will recur. Particles that are heavier, that carry more charge, are less affected by a magnetic field. In fact, you see that the deflection is much lower. Now, we are constantly exposed to radiation. We're constantly exposed to ionizing radiation. And there are multiple sources. You see them reported there. We're exposed to, even now, even here, cosmic radiation. So radiation that comes from the sun, protons. and radiation that comes from outer space. A lot of heavy charged particles close to the iron group. Those are tightly bound particles that travel through space. They do reach us. There's also radioactivity coming from the soil. There are radioactive rocks. There are radioactive construction materials. So most likely the walls of this building are a bit radioactive. Some radioactivity comes out from the soil in the form of noble gases. I guess you know what a noble element is. It's an element that has all the electrons it needs in the outer orbital, which means it doesn't need to bind to other elements. As such, these elements can move through soil by simple diffusion, and they can emerge, and they could potentially concentrate in indoor environments. So in Italy, for example, we have a variety of regions where the soil, the crust of the earth is quite easy, it's quite porous, and the material is called tuff or tuffo in Italian, and the noble gases, and one in particular, radon, can make its way through. And if it concentrates in an indoor environment, breathing it is not a good thing. We'll see why. So air may be radioactive, the soil may emit radiation, cosmic radiation, and you guys are all radioactive. That's the other thing. You are all radioactive. You all contain a variety of radioactive species. By the way, let's define a few words. An element is the smallest amount, is a material that exhibits certain chemical properties, and an atom is the smallest amount of this chemical material expressing certain properties. Atoms contain nuclei, and nuclei are the regions where mass is concentrated, and they're the ones that contain neutrons and protons. So there you see some of the materials of the elements, the varieties that are radioactive. They're called isotopes. We will see what that means, that we contain. That's what's in an adult weighing 70 kilos, the so-called normal human being that doesn't exist, because nobody's the standard human being. Among these, you can see that we have a lot of potassium 40, that is found in a variety of products, food, and many of these things we eat normally. It's famous that bananas contain quite a bit of this. So these are the sources of radioactivity that we contain in our body. And we've seen the other sources. So I repeat them: cosmic radiation, radon, gas, and radioactivity from the soil. These are the four sources of radiation that we're normally exposed to. Then there's a variety of sources that are man-made, artificial sources. We're all familiar with the medical procedures that involve the usage of radiation. So X-ray machines are the basis for radiography, computed tomography, acquiring images of the body following processes from a simple bone fracture to a more complex type of pathology or disease that may be present. X-rays can be used both to diagnose and to treat pathologies. So other types of machines, typically producing higher energy X-rays, can be used quite effectively to treat, for example, cancer, but not only cancer. There are some diseases, for example, tremors, when people cannot control their limbs, they shake uncontrollably, or pain, uncontrolled pain. They can also be treated with targeted radiation sources. And then we have nuclear medicine. In nuclear medicine, what we do is we administer. Am I going too fast, or can you all follow me? Sorry, I need to make sure that you all follow me. Also up there, all of you? Thank you. All right. So in nuclear medicine, what we do is administer radioactive materials to subjects, to patients, in fact. Let me introduce also this difference between a subject, a person that we don't know whether he or she has a disease, and a patient, somebody who has a disease, and investigations are done to further clarify the situation, perhaps come to a course of treatment that is the most appropriate. So again, nuclear medicine is something that can be used. Radioactive materials are administered, and they tell us about the location and the extent of the disease. I'm a nuclear engineer by training, and we do use radiation also to monitor the quality of the components that we use. But not only there. So there are many industrial applications of radiation. Checking the quality of some welding, also detecting the presence of smoke, fire. That can be done using radioactive sources. Some signs, like that exit sign that you there, used to, nowadays no longer very common, used to contain radioactive materials. And then the nuclear fuel cycle. So going from mining to processing of the fuel to using fuel in nuclear power plants, and finally reprocessing or putting the waste into deposits. These are all activities that do cause some release of radiation, some exposure, and some contamination. So here come another couple of concepts that are quite important. Exposure, contamination. Exposure means that radiation comes to us, either crosses our body or stops in the body. That doesn't make us radioactive. Okay, so if somebody goes and has an X-ray done, or a patient goes and receives a radiotherapy treatment, that person will not become radioactive. If instead we incorporate somehow, we ingest, inhale, or we're injected some radioactive material, then we will be radioactive. And again, depending on the type of material, depending on whether it's a deliberate action, so a material is given that will be removed fairly rapidly or not, we will stay radioactive for longer or shorter times. And finally, here comes the thing we all dread, nuclear weapons. So nuclear weapons create this huge blast with a huge pressure wave, very, very high temperatures, the so-called fireball, but also a series of consequences such as the release of radioactive material that is dispersed in the atmosphere. It falls down on the ground, the so-called fallout that people may be exposed to. And what else? The other thing that this radiation emitted from these nuclear weapons can do is expose the soil directly, the ground directly, and render it radioactive. So really a variety of things can follow a nuclear detonation. I believe you'll have a class on these issues. If you agree, I'll review very quickly what atoms, nuclei, and decays are. But again, please don't hesitate. If these things are too basic, I'll skip them. So once again, as I told you, an atom is the smallest amount of a substance expressing certain properties, chemical properties. The name atom, many of you probably know this, means indivisible, something that cannot be divided, cannot be split. We know that this is not true. But again, if we look at this as the minimum amount that exhibits chemical properties, then it is the proper name. Atoms are classified based on their number of protons. So they have this nucleus, the central region where mass concentrates, and the nucleus contains particles. These are either neutrons or protons. Protons carry positive charge, and in a neutral atom, they're balanced by an equal number of electrons. that orbit around the nucleus. Neutrons are there to keep things together, quite simply. When you put nucleons together, such as protons and neutrons, you put them close enough, they attract one another through a force that is called the strong force. On the other hand, if you put close to one another two positive charges, two protons, they'll tend to repel one another. So you understand, protons have both a binding component, that is a strong force, and a component that repulses them, repels them, and that is due to the charge that they carry. So if you put a lot of them together, repulsion tends to prevail. So you need extra neutrons to keep things together. We'll see that for nuclei, for big nuclei to stay together as a cluster of these particles, there have to be more neutrons than protons. Also, you see there the orbits along which we always depict electrons as moving around nuclei. The reality is quite different. It's in fact more beautiful, I would say. Electrons move around nuclei along very complex probability distributions. So these are not fixed orbits, far from those. They're not elliptical, but as you can see, they have beautiful shapes, multiple lobes. What is correct, however, is to define energy levels. They can be, in a way, the orbits or the shells, as we normally call them, over which electrons are found. So electrons are bound to the nuclei depending on their distance from the nucleus. The closer ones are more bound. Of course, they feel the positive charge of the nucleus, and the distant ones are less tightly bound. One more definition. In radiation physics, we do not express energy in units of joule or joule. We express it in units of electron volts. It's a convenient unit. It's the energy, 1 electron volt, that is acquired by one electron as it moves through a difference of potential of 1 volt. Quite simple. You have an electron, you put it in an electric field with a difference of potential of 1 volt, that electron will acquire 1 electron volt. It's 1.6 in 10 to the minus 19 joule, so it's a very, very small amount in terms of joule. It's convenient to use this unit. Also, let's not confuse quantities and units. A quantity is energy. A quantity is distance or length. A quantity is mass. Units are what we use to quantify these quantities, that is, determine the amount. So an electron volt is a unit of energy, a meter, a unit of length, and so on. The energies that we normally encounter in medicine, in diagnostic procedures, are in the order of 100,000 electron volts, or 100 kilo electron volts. So electrons are accelerated by a difference of potential of 100 kilovolts. They acquire 100 kilo electron volts. That's a very typical energy for these electrons. And by the way, what they normally do is they strike a target, tungsten typically, and they produce X-rays. That's how we make X-rays. The electrons, remember we said that charged particles stop. Electrons will stop against this target, tungsten, and as they do that, they will convert part of their energy into X-rays, this electromagnetic radiation, which again we will discuss. So let's put these energies in context a little bit. Here you see a range of values for these energies that we can encounter in, well, somewhat daily situations. So first of all, our molecules, your molecules, are not static. They move. And the energy they have depends on their temperature. At room temperature, which is around 21, but the standard room temperature is around 21, 22 Celsius, molecules have an agitation, a thermal energy of around 400ths of an electron volt. Of course, you gentlemen out there come from the Emirates. Room temperature is a bit of a different issue there. So molecules are much more agitated. But again, that depends on where you are. The photons, the electromagnetic radiation that we can see, have a range of energies that is quite narrow. We can see photons from about 1.6 electron volts to about 1.5 to 3.5. So anybody knows which ones are the most energetic and least energetic of the photons we see? Or rather the colors that we see. What's the range of colors? Perfect. So we can see red, that carries the least amount of energy, has the longest wavelength. We cannot see what's below red, inferior to red, called infrared. Infrared means inferior to red. We can also not see what's beyond violet, that is ultraviolet. That's what ultraviolet means, beyond violet. So those are the photons that we can see. Those are the colors that we can see. If you have a molecule of sodium chloride, which is common kitchen salt, unless you use potassium chloride because you don't want to have a lot of sodium because you have maybe issues with your blood pressure. Anyway, so sodium chloride is an ionic bond. Ionic bond means that one of the atoms gives one of its electrons to the other, and these two can split into ions. You see there the case of sodium ions and chlorine, or chlorine if you prefer. Forgive, I have a bit of an American accent, so chlorine ions. The separation energy is in the order of 4.2 electron volts. Then we also have covalent bonds. Let's go back to high school a little bit. In covalent bonds, electrons, instead of being ceded, given to other atoms, are shared. Those are very, very tight bonds. Ionic bonds are not as tight. Another number that is important, the energy to remove the one electron that hydrogen has. So hydrogen is that element that carries one proton in the nucleus. So it also has one electron moving around the nucleus. Removing that electron, which is called ionization, requires 13.6 electron volts. In general, and now please pay attention to this, in general, removing an electron from an atom requires about 10 electron volts. That's a very small energy, very small. It's 1.6 in 10 to the minus 18 joule, very, very small energy. And yet, as I've shown you at the very beginning, that could be the event that initiates DNA damage. Now you understand why, as we'll see later, we say that there is no threshold, no minimum energy to cause the type of damage that might potentially evolve into a mutation, cancer. You follow? This is a really important point. So the amount of energy that may cause, in a very unlucky situation, that sequela that leads to cancer, in principle, requires a minuscule amount of energy, very, very small. So we assume that there is no threshold, that any amount of energy carried by ionizing radiation can cause that damage. Now, don't get scared. The probability for that to happen is extremely low. We will see that. That is not the main topic of this class, but I will touch upon that to describe how we develop instruments. You will hear more. I'm a radiation biologist by training, so I like this topic. But again, you'll have classes on that specific issue. You're all very young, lucky you. So I don't know if you've ever seen a TV set with a cathodic tube. You've also, or have you only seen the flat panels that are common nowadays? Yeah, you're smiling at me. Yeah. So I grew up with these big TV sets, the big cathodic tubes. And inside those, electrons were accelerated from one side to the other. They were striking the inside of the screen and producing the image. My mother was telling me, don't stand so close to the screen. And she was always saying that. And she was right. She was right, because when you strike the screen, the inner part, with electrons, which were accelerated by 20 kilovolts, so they had 20 keV, they were producing a bit of X-rays. Now, the screen itself was a fairly thick layer of glass, which does attenuate them significantly, but again, X-rays are not ever brought to zero. They're attenuated. So in principle, a little bit was coming out. I point out that 20 keV is also the energy of the X-rays that are used in mammography. So that is an energy that can penetrate the body. Of course, it penetrates the breast, which is compressed, which has no bones, which is glandular tissue and quite a bit of adipose tissue, which means easy to penetrate, but still they go through that. So again, it's nothing to play with. We do use, as reported there, a fairly wide range of energies in diagnostic radiology. They go from 20 keV, again, mammography, up to 140. That's the upper limit of the energies used in computed tomography. Once we look at the radiations coming from radioactive processes, the values are much higher. You can see there. Gamma rays, typically several MeV, million electron volts. Beta particles, similar range. Alpha particles, easily up to 10 million electron volts. And hold yourselves now, you're presently being crossed by cosmic rays, and their energies are up to 1,000 tera electron volts. Look it up. It's a huge number. It looks scary, but the good news is they're so energetic that they go through everything. They really do. So they virtually have no interactions. And they do, it's not good news, but again, it's a very, very rare event. Think of this. Some of them are so penetrating that if you want to study certain types of these radiations, called neutrinos, you have to do it under a mountain. So in central Italy, not far from here, we have a laboratory under the biggest mountain of central Italy that is called Gran Sasso, which means the big stone. And again, a nuclear measurements laboratories is under this mountain, and the mountain serves as a filter to attenuate other types of cosmic radiation. Think of it. All right, so nuclei. When I teach, I normally take breaks, maybe short ones after an hour or so. If you like me to do that, I'll be happy to. So again, if you need a break, a coffee, please don't tell me you're going to smoke. But if you need a break and a coffee, I'll be happy to make it. Yep. What you see there is the so-called chart of the elements. The black solid squares represent stable nuclei, nuclei that are happy with their structure, that don't want to change. And then you see a lot of open squares and some red squares. So the open squares are the unstable nuclei, those that instead wish or need to become something else. And those are artificially made. They're man-made. Most of them for medical purposes, but not all of them. And then you see some red squares. Those are naturally occurring radioactive materials. You'll see that they're all up for very, very high masses of the nuclei. And those are typically alpha particle emitters. Are you familiar with the concept of radioactivity? You heard of it? So radioactivity is simply what nuclei do when they try to become more stable. So if they're not stable, they have excess energy or they have excess particles inside, they want to get rid of them. If you have questions, please stop me, okay? So raise your hand, wave, I'll try to answer, okay? So once again, nuclei are not all stable. I pointed out that several are man-made and they're radioactive. Others are naturally occurring radioactive nuclei. What they want to do is become more stable. Now, if I had something that I could drop without breaking it, I would put it here on the edge of this table, push it a little bit, and that object would spontaneously move and fall on the ground. That's because when it's here, it has more potential energy than when it's down there. Then it would move, accelerate, and go towards a situation of lower energy content, lower potential energy. The concept is similar. When you encounter or create nuclear structures that lie on the two sides of that valley there, those want to fall from the table to the ground because they will be more stable that way. They will not necessarily become stable, they will just become more stable. Sometimes they need multiple steps to become truly stable. Sometimes they need to get rid of a negative charge, sometimes of a positive charge, sometimes of energy, that's all. A positive charge would be an alpha particle, a negative charge, a beta minus, we will see that, and energy would be a gamma ray. So alpha particles, let's look at that. It's the simplest type of decay for many reasons. And it's also the one that happens in nature, in those nuclei that I mentioned, those red squares up there, for masses greater than 210. When I say masses, I mean the combined number of neutrons and protons. That is the so-called mass number of an atom, of a structure that we're looking at. So alpha particle decay. We start from a so-called parent nucleus. In that case, it's uranium-235, which, by the way, is the one that is used in nuclear power plants. It's also used to make bombs. By emitting an alpha particle, which is a cluster of 4 particles, 2 protons and 2 neutrons, emitting this cluster, the nucleus changes. As you can see, the mass number changes from 235 to 231, because the alpha particle carries 4 units of mass, 2 protons and 2 neutrons. Now, this is a process that happens in nature. It happens a lot. And one relevant case is the one shown there. That is the decay of radium-226 into radon-222. That is what I mentioned before. That is the noble radioactive gas that emerges from the crust of the Earth, and that if we inhale it, because it emits alpha particles, can do significant damage, biological damage. So let's also touch upon the concept of biological damage. Biological damage happens in the presence of 2 circumstances: very damaging radiation, very sensitive tissues. The combination of these 2 is what enhances the biological damage. So radon emits alpha particles. Alpha particles travel a very short distance, very, very short, tens of microns in tissue. So talk to me a little bit. Which are the tissues that you think will be exposed to the alpha particles from radon? Skin. The skin, very good. We have about 2 square meters of skin. That's a lot of, it's a lot of surface, isn't it? Which other surface? The eyes. Okay, very good. One more. The lungs, very good. We have a lot of square meters. I think it's about 50 of lungs. But the issue is not the surface. The issue is the type of tissue. So let's look at the skin. Do we know how the skin looks? So the skin has a dead layer of about 70 micron dead. It's a good thing. It looks disturbing, but it's a good thing that we have a dead layer of skin on our body. Otherwise, when you put your elbows on the desk, you would bleed. You would bleed. If your cells were alive all the way to the surface of the skin, they would be immediately damaged by any contact with anything. So we have this protective layer of dead skin cells. And at 70 micron of depth, we have the so-called basal layer, where new cells, new skin cells are produced. Now, alpha particles from radon do not travel 70 micron. So yes, it's true that the skin is exposed, but nothing happens because the alpha particles cross dead cells. It's very different when it comes to the lungs. So radon is a noble element, which means it doesn't react. It also means that it doesn't stick to anything. We breathe it and it goes into the lungs easily. It decays. Now, what about the lungs? Do they have dead cells on the surface? No. Why not? Exchange. Yeah, absolutely. So the lungs are very, very alive and very lively, in fact, all the way to the surface. They have to exchange oxygen. So the hemoglobin captures the oxygen and then it carries it around. You know, the blood does a lot of things. It carries oxygen, it carries nutrients, it removes garbage. It's our sewer system. So we don't really think of it this way, but it's not necessarily the cleanest environment of the that we have inside. So anyway, the blood does these things. So lungs have to be alive all the way to the surface. So now we have a combination of cells that are very lively and particles, these alpha particles that have a very high ionization density, that cause a very high ionization density. That's a bad combination. Have you seen the movie The Perfect Storm? You haven't? Come on, some of you must have seen it. Okay, it's like a perfect storm, combining alpha particles and lung tissue. Lung tissue does something else that should be mentioned. Like other tissues in our body, it replaces constantly its cells, constantly. So the lining of our lungs, the mucosa, are constantly replaced. And it also happens in our gastrointestinal system, our GI tracts, esophagus, stomach, intestines. They are lined by cells that are constantly replaced. Do we know why? Those cells, superficial cells, are exposed to external agents. And these external agents may be toxic. So in order to prevent damage, they replace themselves. The irony or sad part is that by replacing themselves constantly, they do protect themselves from chemical attacks, but they become more vulnerable, more susceptible to radiation injury. Because radiation is particularly damaging when our cells go through mitosis. Mitosis is the splitting of the cells, the division of the cells. So again, inside our body, we have systems that are lined by cells that are constantly being replaced, the GI tract, but also the respiratory tract. And those cells are very, very sensitive. That's one category of sensitive cells. Other cells that are very sensitive are those that produce something. Can you think of a system that produces something constantly? That's one of them. Very good. So that's a gland. Glands do produce something, all kinds of things. There's another one that is very, very important. Very important. Absolutely. The bone marrow, that is our hematopoietic system. It constantly produces blood, constantly. And the blood is fundamental not only because of what we mentioned before, that is bringing oxygen, bringing nutrients, removing waste. It also forms our immune system. So we have leukocytes in particular, the white blood cells, that attack what attacks us, or at least they should. Sometimes it doesn't work because they don't recognize an attack, and then they allow things to grow, say cancer. Anyway, we'll get to that. So here I took a detour, I apologize. We were talking about radium and radon. You see them there. And what you see there is, in fact, a so-called radioactive series. That is, you see a series of nuclear structures that evolve into one another, that decay into one another. There are 4 of these radioactive series, and they all end with stable nuclei, stable isotopes. 3 of them are different varieties of lead, and 1 is bismuth. Isotopes, by the way, we'll have to define them. Isotopes are nuclear structures that only differ in the number of neutrons. So from a chemical point of view, they have the same properties because their chemistry depends on the number of protons and the number of electrons. That's fixed. If you were to change that number, which is called atomic number, it would be a different element. But you can change a number of neutrons, and you have so-called isotopes. The naming grid, by the way, means that they occupy the same space in the periodic chart of the elements, because that chart lists the elements in terms of their chemical properties. Are you ready for a break, or should I continue a bit more? You tell me. I don't want to lose you, okay? I'd rather take a 5-minute break and then continue, but the class is for you. So you tell me. I take no offense. 5 minutes? 5 minutes.
Il 9 ho l'esame del quarto qualificato.
Mi auguro che le siano utili. Quale livello? Avete un sacco delle competenze di base che sono fondamentali.
Sì.
Per cui non lo dica come fosse un limite, secondo me è un vantaggio. Secondo me è un vantaggio. Bene.
Molto. Proprio stamattina. C'è la lezione online.
Bene, bene. Sir, morning.
How are you?
No, that's how about yourself? Where are you from, sir?
I'm from Syria.
Okay. Yes. I know where the place is.
Oh.
I wish I had been there, but I know where the place is.
Oh.
And are you liking it here so far? Things are going well?
Yeah. One day you'll be here.
Pardon?
I said one day you'll be here.
I would love to. I would love to. Never been to that part of Africa. It's in the very north, the very south, but not in between. Shame on me. Shame on me. All right.
You are talking about research.
Yeah. I have a lot of projects. As we go through the different topics, as we think, as we go through the different topics, I'll make sure to point out when things are part of the activities that I do research. Well, I do research almost everything that I do.
All right.
Some specific topics, radiobiology, so-called biodosimetry techniques to estimate the radiation dose to people who have accidents or who do not wear dosimeters. I also do security applications, detector development, all these things. So
I'll be interested.
sounds good.
Yeah. So,
Sounds good.
yeah. For completing this course, I would like to do maybe few, 2, 3 publications. So you can give me some topics. So
Sure.
do something.
Sure. Maybe you let me know what you do back home, what kind of facilities you have, and we'll find topics that can be developed or that you can do here in Italy while you're taking this course, or something like that. Yeah, excellent. It'll be a pleasure. Devo trovare il modo di inclinarlo di più, perché sono fuori misura e quindi per come lo osservo è tutto sbiadito. Lo schermo, intendo. Ora ci stai?
No, no, ok, perché di solito mettiamo una cosa sotto e lo rialziamo.
Quello non sarebbe male. Aspetta, con questo?
Esatto.
Con questo?
No, così però vola. È precaria la
Ci fidiamo?
Mm,
Non tanto, eh.
vabbè, dai, però
Senti, io non lo tocco
un
più.
male che va, esatto, va per terra.
No, dai.
No, ciao. Dai.
Allora,
Meglio?
però per lui sarà impossibile più bassa. Non potrei volare,
Come faccio fare delle facce dei numeri?
sono iscritte dov'è?
Sì, molto leggero.
Perché non so dove si vengono. Ah, ok.
Domani. Facendo gli esami. Quindi che sei? Come 42. Vedo?
Grazie.
La dico sicuro, sì.
Professore, professore, buongiorno. Lei probabilmente conosce mio fratello è Daniele Franci.
Sì che lo conosco.
Daniele, sì, lavora, anche lui è nel live.
E da tanto pure.
Sì.
Bene.
Sì. Poi quando ho visto che anche lei è, insomma,
Sì, io sono coinvolto nella scuola.
sì, me l'ha detto. Ho avuto parole nei suoi riguardi veramente insomma, un fiore all'occhiello del professorone. Ha detto,
Devo dire che da lui è gratificante.
No,
E tuo fratello sa quello che fa.
sì, no, sono d'accordo con lei. Infatti io cerco sempre di prendere esempio da
Bene, è
Daniele.
bellissima questa cosa. Bella. Quindi l'idea di fare questo master.
Ma io in realtà perché io sono un chimico a differenza di io ho studiato proprio qua a Tor Vergata, sono laureato in chimica magistrale. Io adesso lavoro nell'esercito, sono un ufficiale dell'esercito. Sì. Quindi appena si è presentata l'occasione di fare questo master lo racconto subito.
Basi in chimica sono preziosissime per queste materie.
No, poi in realtà cioè la facoltà di chimica a Tor Vergata è molto, diciamo, eterogenea, cioè, secondo me un pochino, come posso dire, non è la classe, cioè, per esempio, chimica della Sapienza è molto più legata all'inorganica, a reazioni, invece a Tor Vergata è molto più chimica fisica, poi io ho un background di chimica fisica. Sì, quindi no, infatti fortunatamente insomma sì, no, mi trovo abbastanza nel mio ambito.
Perfetto. Veramente piacere.
Grazie.
Il problema dei 5 minuti è che it's never 5 minutes. Ho la sensazione, ti lascio un messaggio perché sono nella pausa qui della lezione. Ho la sensazione che per il generale Sirmarco non sia un problema eventualmente incrociarsi con un'altra delegazione. Comunque lui mi ha parlato di poter partire intorno a mezzogiorno, che significa arriverebbe tra le 3 e le 4, penso. E magari gli confermo che quello che lui aveva in mente a voi va bene, d'accordo?
Uso, fino al secondo livello, dove si deve? Alzate le mani. Qualcuno quelli che sono
Let's restart. So once again, we've introduced the concept of alpha particle decay, quite important. And let's look at this decay scheme that is shown there. That is indeed the decay of radium-226 into radon-222. As you can see, there are two arrows. And by the way, they point to the left, which is the convention that we use when a nucleus loses positive charges. So because the nucleus loses 2 protons in decay alpha, it's a net loss of positive charges of atomic number, and the arrow points to the left. We'll see that in beta minus decay, where the number of protons, positive charges, increases, the arrow points to the right. Now the arrows are 2. One goes straight to the fundamental state of radon-222. It's a direct decay. And the other one has an intermediate step from which a gamma ray is emitted. Question for you, what do you think we have in that excited intermediate step? Do we have Radium, still, or radon? That nucleus that finally emits a gamma ray to reach the fundamental state, is it radium or radon already? It's radon, that is correct. The alpha particle has been emitted, the change has occurred, that's already radon, but it's excited. It has excess energy and it decays by emitting a gamma ray. We'll see that it's not the only thing that can happen. All right, in the alpha particle decay, we start from one particle and we end with two. So it's a two-body process. Now, without getting into too many details, and I promise I'll spare you mathematics, but we have two conservation equations. What's conserved is so-called momentum, that is the product of mass and velocity. And the other thing that is conserved is the energy, the kinetic energy. For the alpha particle decay to be possible, there has to be some available energy. Conventionally, that is indicated by the letter Q. That's called the Q value. So you see the letter Q that converts that energy into the kinetic energy of the two products, the alpha particle and the daughter nucleus. And the other one is the conservation of momentum. That there are two variables, two unknowns, and two equations. So we have a single solution to this system of two equations. That's why the spectrum of emission of alpha particles is a line spectrum. It's a discrete spectrum. The alpha particles come out with specific energies. Well, sometimes there's a second one because there's that intermediate step. For example. But they're lines. They're not spectra, continuous spectra. So once again, that's because we have two conservation equations and two variables. In reality, we never say that, but there's something else that is conserved in nature. Can you think of something else that is conserved? It is charge. Very good. So the charge is conserved. We always take it for granted. We never mention that explicitly, but that third equation should be there, conservation of charge. All right. So before we said that when nuclei are big and heavy, in order to stay together, they need more neutrons than protons. Here's another graph representing that. You see there's a straight line that is the so-called line of equality along which the number of neutrons and of protons is the same. But you see that for larger nuclei, the actual line of stability bends towards a greater number of neutrons compared to protons. So once again, you need more neutrons than protons to keep things together. Now, if you manage to create a nucleus here, not on the line of equality of stability, but here, then you'll have too many neutrons. If you produce somehow a nucleus that lies here, that'll have too many protons. So let's look at this case first. It's easier. The neutron-rich side. If nuclei are artificially produced with too many neutrons, they will want to get rid of some of those neutrons. And the easiest way to do that is by emitting a beta particle, beta minus instability. In this case, the process looks like this. Now you see the difference. There are three particles involved. It's a three-body decay process. Of these three particles, one is very heavy, the daughter nucleus. In this case, calcium deriving from potassium 40. And two are very, very light. This should be the Greek letter nu. That stands for neutrino. Sorry, I'll have to edit that. And that actually reminds me of one rule that we follow. The radiations that come from radioactive decay processes are indicated by Greek alphabet letters. Alpha, beta, gamma, nu, the neutrino. There is an exception, we will see that, the delta ray, but again, we'll talk about it later. So once again, three bodies, the daughter, the neutrino, in this case it's an antineutrino, and the beta minus particle. By the way, anti means that if it meets what we call a neutrino, the two of them disappear. This concept of matter and antimatter is not science fiction. A beta minus particle and a beta plus particle, a negatron and a positron, if they encounter, they disappear. They become energy. So you have Einstein's equation at work in that you have the conversion of mass into energy. We will see that. Now, the beta particle and the antineutrino have extremely small masses, very, very small. So let's go back to those two equations. Conservation of momentum, conservation of kinetic energy. There's a third item that is missing here for the beta decay, but the point is, whenever you have the product of mass and velocity, and one of the particles is very massive, like this one, its velocity will be very, very small. In fact, the intensity of the velocity, which is called speed, but let's not get into too many details. For the conservation of momentum to occur, this particle that has a very large mass, thousands of times larger than these, in fact, tens of thousands of times, these instead have very small masses, so they will have very high speeds. In other words, the speed, the velocity, the kinetic energy mainly goes to these very small particles. Very little goes to this. Let's keep that in mind. We'll need it in a second. Here you see examples of these decays, and you see that also in these cases, you may have intermediate steps. This is cesium-137 decays into barium-137. Here's an excited state of barium, now we understand. An excited state of barium, it decays by the emission of a gamma ray to the fundamental state of barium. In other cases, you have the direct transition from the cesium-137 to barium-137. Let me also tell you this. Cesium-137 is one of the radioactive isotopes that come out in case of the occurrence of a nuclear accident or the detonation of a nuclear weapon. Emitted isotopes will be cesium, large amounts of emitted isotopes will comprise cesium-137, strontium-90, iodine-131, cobalt-60, and these are all beta minus emitters for reasons that we may have time to touch upon. This is another case. This is the decay of phosphorus 32 into sulfur 32. It's a direct transition. Let me go back to the concept of the fact that we have three particles and two conservation equations. Three bodies, two unknowns, two equations, three unknowns. The system of two equations allows infinite solutions now. It's ill-determined. And the consequence is that we don't have a line spectrum anymore. We have a continuous spectrum. So beta particles do not come out with discrete single energies. They come out with a spectrum. And now you also understand why here they show the energy of the beta particle and the energy of the neutrino as the only components, because they neglect the little energy that goes to the massive daughter nucleus. If it's unclear, you ask me, I'll go over it again. The concept is the energy goes to the very light particles, because again, the conservation of momentum requires that. All right, so that's beta minus decay, which in principle corresponds to a neutron becoming a proton. Neutrons and protons are both in the nucleus. They have very similar masses, but the neutron is a bit heavier, a bit more massive. And in general, a trend towards greater stability implies a reduction in mass. So the process of a neutron becoming a proton is a spontaneous process. And that is, by the way, the reason why on Earth we're not exposed to neutrons coming from the sun. The sun emits neutrons. The sun emits protons, it emits neutrons, it emits helium nuclei, but neutrons decay before arriving to the Earth. So you know the planets that are encountered before the Earth. Do we know which planets are encountered before the Earth, between Earth and the sun? Very good. So Mercury is a planet around which NASA has been doing radiation measurements. And they have detected the presence of neutrons from the sun, but they don't make it much beyond Mercury. They decay. And yet, on Earth, we are exposed to neutrons. When we fly, we are exposed to significant amounts of neutrons. Those neutrons are not cosmic neutrons. They don't come from outer space or the sun. They are so-called cosmogenic neutrons, which means they are produced in the atmosphere by interactions between other radiations and the atmosphere. So all these particles that arrive towards the Earth and interact with the atmosphere is a wonderful shield. Are there any engineers around here? Very good. For us, engineers, what is one atmosphere? Yes, it is. But what are the units that we use because we like to keep it simple? Well, okay, then I keep it simpler. For me, an atmosphere is 1 kilogram per square centimeter. Okay, it's a bit brutal, but 1 kilogram per square centimeter. So now imagine a square centimeter. It's a teeny tiny thing like this. How tall do you think a column of water has to be to produce 1 kilogram if the cross section is 1 centimeter? 10 meters. Does any of you do scuba diving, go underwater? Come on, you guys. All right, wonderful. So you know very well that each 10 meters of depth correspond to 1 additional atmosphere. So what is the story? The story is that the atmosphere, the air above us, is equivalent to 10 meters of water. That's a pretty thick shield. Think about it. It's a lot of material that in fact attenuates radiation, cosmic radiation, but it also produces some other radiation because in the interaction between cosmic radiation and the air, particles are produced, in particular neutrons. The maximum number of neutrons is produced at a height of about 20 kilometers from the surface of the planet. That is why when the Concorde existed, does anybody know that there was a hypersonic aircraft that was created together by Britain and France in a sign of agreement, Concorde? So that guy was flying at about 17, 18 kilometers of height. People on that flight were exposed to significant amounts of neutrons. It's the only aircraft that used to carry a radiation detector for that reason. Had there been a solar flare, sometimes the sun gets a little antsy, gets excited. It gets excited and it emits more radiation. When the Concorde was flying, had a solar flare taken place, the Concorde would have had to take countermeasures. What do you think it would have done had it detected? Oh, well, how would you do that? Well, but these are neutrons. Yeah. So what it used to have to do was descend so that more atmosphere would have been above it and more shielding. You understand? Because the higher you go, the lower the amount of air you have on top, and therefore the lower the amount of shielding. So that aircraft had detectors, and had there been an event of that kind, it would have descended to increase the amount of atmosphere above. Hey, don't say it would have gone down. It has a different meaning in English, okay? Descend is to lower the altitude. Go down means to crash. All right, so it didn't go down. It descended. All right, so that's what it would have done had there been a solar flare. I don't think it ever happened, or rather, it never happened requiring for the plane to descend. Okay, so this was beta minus. We may also have beta plus, that is, when we have nuclei that are here, typically artificially produced, they have too many protons. But now you understand, turning a neutron into a proton is something easy. It happens spontaneously. Turning a proton into a neutron means making a lighter particle become heavier. That is not favored in nature. For that to happen, to keep it simple, you have to pump a lot of energy into the process, a lot of energy. So this type of change, decay, only happen when the excitation level, that Q value that I mentioned before, is very high, more than 1 MeV. That's a lot of energy. And then this is what happens. We have the parent sodium-22, for example, becoming neon-22. By the way, the mass number has not changed. Had you noticed that? It has not changed because here a proton has converted into a neutron, but they're both nucleons. So the number of nucleons has not changed. One changed color, so to say, but it's still a massive particle. Anyway, so 22 remaining 22, but the element is different. This one had more protons. This has fewer protons. This is the process. See, fewer protons. This atom X with atomic number A, with mass number A and atomic number Z has become an atom with atomic number Z minus 1, or Z, if you say Z. So it has fewer protons. It's a different element. Okay. This thing that looks weird is something that we use every day in medicine. Positron decay, the emission of a positron, is what happens in a procedure of nuclear medicine called positron emission tomography. And here's how it works. A nucleus that is radioactive and emits positrons is used, typically bound to a molecule that is given to the patient. As it decays inside the patient, it emits positrons. Positrons lose energy. They stop. When their energy is very low, they encounter a negative electron from the material around it, and the two of them disappear. They annihilate. And in their place, you get two photons. So you have mass converting into energy, mass becoming pure energy with no mass. When the positron annihilates with an electron, they have virtually no energy. So their momentum is how much? If the energy is almost zero, the velocity and the speed are almost zero. So the energy is also almost zero. So the only energy that goes to the two photons is the one corresponding to the mass of those particles. And that is 511 keV. So we get two photons. They come out in opposite directions because you have to have conservation of momentum. So the two photons, as they're emitted in opposite directions, and they cancel out their momentum. You follow? I hope I'm not going too fast. The point is, conservation of energy, mass, and momentum leads to the fact that following positron annihilation, we get two photons. They come out in opposite directions with the same energy. That's why we can use it in medicine. Because when a patient receives a material emitting positrons, we get these pairs of photons coming out in opposite direction. We record them with a ring of detectors. They arrive almost at the same time, within a few nanoseconds of one another. And so we record the pair of photons, and by recording many of these events, we can reconstruct the position where the radioactivity was taken up, where it concentrated, and that indicates the presence of a problem. I said it very quickly, I know, but I teach courses on this stuff. I don't have the time to do that. So But the concept, I hope, is clear. The concept is,
So by recording the delay of the difference time to reach from the source to the detector.
yeah, that's sophisticated. So sometimes you can actually record the delay between the arrival of the two photons. It's called time of flight. That's a very sophisticated approach. In general, you record both of them and you're happy if you can get both of them. If you were able to measure the different arrival times, that would help you in the reconstruction. It would make the estimate of the position of the source more accurate. That's pretty advanced. So there's really no time for that. Sorry. But anyway, the point is that this is used in medicine. Okay. So we've seen many, many different types of decays. And yet they have something in common. The way a radioactive material disappears over time always follows the same trend, the same law, the same exponential decay. This is the exponential decay. What you see here is the ratio between what we call activity. So let's look at it this way. If you have a nucleus and that nucleus disappears, because of the radioactive process, something is emitted while the nucleus disappears. So you can look at the process in terms of disappearance of the nucleus or emission of radiation. The disappearance is called decay. The emission of radiation is called activity. It's the same thing. One is negative of the other because one disappears and the other one appears. Is that clear? Okay. So here the curve is expressed in terms of activity. And you see the plot gives you the ratio between the activity at any given time and the initial activity, A naught, or A sub zero, however you pronounce it, you prefer to pronounce it. And the interesting thing about this curve is that you can identify a characteristic time, which is called half-life. Corresponding to each one of these half-lives, the activity is cut in half. So after the first half-life, the activity drops to 50%, the second one 25, 12.5, and so on. So you understand, if you know the half-life of your material, you can estimate quickly how much radioactivity you still have based on how much time has passed since you started measuring it. Let me skip this part, otherwise it'll take forever. So let me show you how we derive. This is easy. I promise it's easy. How we derive the exponential. The assumption is that the number of nuclei that decay, that change in a given time interval, delta t, is proportional to that number. The number that decays is delta n, is proportional to the number of nuclei that are present. N is proportional. We can write the proportionality this way with a negative term because it's a loss of nuclei. Nuclei lost in sorry, this should be a delta t. Let's turn that into a differential equation. So the number of nuclei lost per unit time. Instead of delta, we have dt. It's a differential. It's a very short time now, not a delta t finite time, but a dt very, very short infinitesimal time. This is now a differential equation. We can integrate it, and this is the solution. So this is the number of nuclei you still have, the initial number of nuclei, and that's the number that gives you how many of the nuclei you still have, the fraction that you still have. So that is the surviving number of nuclei. Now, that's again, the same equation. If we take the opposite is the activity. Every time you lose a nucleus, you're gaining some radiation coming out. So it's the same thing, but we changed the sign. So radioactivity, which is the quantity, used to be measured in units of Curie. Madame Curie studied radioactivity extensively, and her estimate was that 1 gram of radium, the same radium that we mentioned before, radium-226, that 1 gram of radium underwent 3.7 in 10 to the 10th disintegrations, so radiation emissions per second. This is not exact, but she was pretty close. And considering the tools at her disposal, this was not bad at all. It's really 3.61, but it's very, very close. In her honor, the unit Curie was introduced, 1 Curie being something that emits 3.7 in 10 to the 10th rays or particles per second, the activity of 1 gram of radium. In the International System of Units, we use something simpler. That is, we use the becquerel. Becquerel is the gentleman that discovered radioactivity, by the way. And 1 becquerel is 1 change or disintegration per second. So you can also say that 1 Curie is 3.7 in 10 to the 10th becquerels. Okay? In medicine, medical doctors are somewhat conservative. In medicine, they still use the Curie and the millicurie. So typically, when there's a nuclear medicine procedure, they say that they're giving 10 millicurie, that's the standard, of whatever material to a patient. Okay? So once again, also in the United States, they still use the Curie, also pretty conservative place. Curie for medical doctors, Curie for US scientists, we use here in Europe and in the rest of the world, really, the becquerel. Comments or questions? Please make them freely. No? Okay. So what do we encounter? Let's see some radioactive materials that we may encounter and also their applications. You see how many they are, and this is a partial list. Cesium, cobalt, plutonium, iridium, hydrogen, tritium, that is hydrogen 3, strontium 90. And also shown there is what they're used for. If you use cesium, for example, to irradiate food, you need a very, very high amount of radioactivity. Did you know that a lot of the food you eat has been irradiated? You didn't? Okay. For example, your onions, garlic, potatoes are all irradiated so that they will not sprout, they will not germinate quickly. Otherwise, they will go back very quickly. One way to make them last longer is to irradiate them first. And as I said before, they don't become radioactive. Radiation goes through them. They're not radioactive, okay? And in fact, even their taste doesn't really change. So people have tried, there have been blind tests, people checking onions and potatoes that have been irradiated or not, and could not tell the difference. It's one of those things that not everybody knows. Later, I'll show you more things that we may not necessarily know as I show you the different perception of situations and risks between experts and the layman, the public. All right. So once again, those are some, you'll get this material, by the way. So those are some of the radioactive sources and some of the activities that are used. Before I mention the 4 radioactive series or families, you see this one. This one in theory starts with plutonium, but everybody calls it the uranium-235 series. This one starts with thorium-232, but I really wanted to show another one. I wanted to show this one here, the one that starts with uranium-238. Look at the half-life of uranium-238. Can you read this number? 4.5 giga or billion years. That is the age of the Earth. That is in the non-religious estimates, how long the Earth has existed. I respect everything. So if you think it's 4,000 years old, fine. But scientists believe that it was created, or it started existing, let's say, 4.5 million years ago. That is exactly the half-life of uranium-238. So how much uranium-238 do we have today compared to the beginning? Exactly half of it. Exactly half of it. Let's go back to the other series. This one, in principle, starts with plutonium-239, which is infamous because it's used to make nuclear weapons. Now, the half-life of plutonium-239 is 24,000 years. Do you think there's any left from 4.5 billion years ago? No, there isn't. So the only plutonium that is around is the one that was produced artificially to make weapons. And that's, that's all of it. That's the story of it. So we call this series as the uranium-235 series, exactly because there's not much of the original plutonium. Okay, then comes the one that starts with thorium-232, and the other one, the final one, starts with neptunium-237. And as I mentioned before, they end with stable isotopes. This is lead-207, this is lead-208, lead-206, and bismuth-209. Okay, these are the stable isotopes that represent the end of those series. Let me tell you why I've talked about these series. When you have a radioactive decay of one species, this is the same, the equation that we've seen before, and this is the solution, okay? And I'm sorry I changed the font, so this should be a lambda. I'll fix it before I distribute the material. Lambda is the exponent of this exponential. It's called decay constant. So we're losing some of that. And then we have another equation for the daughter. Now, the daughter is produced by the decay of the parent. So what we lose of the parent is what we gain of the daughter. See, it's the same thing, but we change the sign. And then the daughter decays, so it has its own negative term. So now we have two equations in this system of, it's a linear differential equation system. That is the solution. Trust me, that's a solution, okay? I will not derive it for you. But I will look at one interesting case, simple to look at and important. It's the case that we call secular equilibrium. It's the case in which the parent has a half-life much longer than the daughter. An example is exactly radium becoming radon. Radon has a half-life of 1,622 years. Radon has a half-life of 3.8 days. Huge difference, okay? The decay constant is proportional to the inverse of this. So if T1 is much bigger than T2, lambda 1 is much smaller than lambda 2. Let's look at the implication of this. This is the solution for that system. Here we have lambda 2 minus lambda 1. What do you think? Can we neglect lambda 1? Yes, we can. So we simplify this and write lambda 2. And here, because lambda 1 is much smaller than lambda 2, this term disappears very quickly. So we have a simplified, and this is the end of the mathematics that we will use, I promise. We can simplify the previous equation into this. If we rearrange the terms, what we get is this, which means the activity of the daughter is equal to the activity of the parent. So in a secular equilibrium, the parent has a very, very long life, so the activity doesn't seem to change, and the daughter approaches the parent until they become the same. This is something that we do encounter. In medicine, for example, we encounter it in nature. It's an important case. It's called secular equilibrium. Here come two examples. Not only radium and radon, but also strontium-90 that decays into yttrium-90. This is used as a source for radiotherapy. It's used to treat cancer of the eye, because these particles travel exactly the distance that hits cancer in the eye. Okay, so that's for radioactive decays. And soon we're going to make another break, I think. So what have we seen? We've seen nuclei that are excited. When they're excited, they may emit gamma rays. or they actually can eject an electron. The energy, in other words, can be given to an electron. And then we have atoms that may be excited. An excited nucleus emits a gamma ray, or what we call conversion electron. An excited atom is one that has a missing electron in one of the shells. That missing electron will be replaced by one from another shell, and the process will result in the emission of a photon also. This we call X-ray, this we call gamma ray. And that is the point I want to stress. We call gamma rays the photons coming from nuclei, from radioactive decays. We call X-rays the photons coming from the electron shells, changes in the electron shells. Please pay attention to this point, because often people say an X-ray is a low energy photon, a gamma ray is a high energy photon. That is wrong, okay? A gamma ray simply comes from the nucleus, an X-ray comes from the electron shells, changes in the electron shells. That's all I care to stress. A couple more comments. The cosmic radiation, the showers, as they're called, that it produces in the atmosphere. The point that we've mentioned before, between Earth and Sun are Mercury and Venus. Neutrons don't make it to the Earth, they decay before. You can actually calculate how long it takes for neutrons to reach the Earth. You'll get this material. You can do the math if you wish. It's time for me to accelerate a little bit. Plus, I've already mentioned these comments. And this is the intensity of neutrons at different heights from the ground. The maximum is at about 18 kilometers. So that is where you get more neutrons. That is also where the instruments on board of an aircraft may be damaged by radiation, because that's another thing to keep in mind. Radiation not only can cause biological effects, it can also cause effects on devices, electronics. So aircraft that were flying at 20 kilometers had more of this damage, but the flight was much shorter. So, things sort of compensate. I mentioned this issue of cosmic radiation interacting with the atmosphere because one of the interactions shown here is between a neutron and nitrogen-14, and that produces carbon-14 in the atmosphere. So when we breathe the air or otherwise incorporate this carbon-14, we add another radioactive material in our body. When we stop breathing, we're no longer alive. We don't accumulate more of this carbon-14. So it's possible, by looking at the amount of carbon-14 in fossils, in what's left of animals, living beings, it's possible to estimate when they died. It's called dating. It's called carbon-14 dating. So you see how many applications there can be in radioactive decays. All right, next topic is how these radiations that we have described interact with matter. That's the first step to detecting. Let's see how they interact with matter. We have two possibilities. One is an electron is removed completely. It's called ionization. Another possibility, an electron jumps from one orbital to another. That's called excitation. When radiation goes through matter, an electron, for example, it produces what we call a track. As it moves through matter, an electron or another particle can cause ionizations or excitations. And those are the events that may lead to biological damage. So I'll repeat it. You have a particle that goes through matter. That particle causes ionizations and excitations. These can lead to biological damage. Sometimes, along the track, you see an additional track that is created on the side. When that happens, we call it delta ray. And that is the exception that I mentioned before. It's the one case when we use a Greek alphabet letter, but not for a radioactive decay. Let's look at how different radiations interact. This is an alpha particle that moves through many atoms. The alpha particle is here. You can think of these as pictures taken at regular intervals. Regular intervals. If you take pictures and you see this, what does it mean? It means that at the beginning, the particle is moving fast. It covers a long distance. And then it travels much more slowly. You follow? At the end of its path, it takes 2 electrons from the other atoms, and it becomes a full atom of helium, helium-4. So this is what happens when you shoot alpha particles through matter, for example, through the lungs or through the skin. And this is proof that it's true. This is a so-called autoradiograph. If you take a material that emits alpha particles and you put it in contact with a detector, you can take a picture of these alpha particles. In this case, it's what happens when a piece of bone of a rat that had been breathing americium, a piece of bone is put in contact with a radiographic film. You follow? This is called autoradiograph. And what you see are the tracks of 2 alpha particles that are indeed straight lines. They are straight lines because the alpha particle is so heavy that when it moves through matter, it goes straight, and the electrons that it interacts with are scattered, are pulled aside. This is very important. So heavy charged particles move straight, and they ionize the material that they move through. Here's the proof. Sometimes calculations are made of the path of the particles. They're called Monte Carlo calculations. I'll show you some examples. They are calculations where you associate the probability of different events for a particle that moves through matter, and you simulate its path. Take it like this. So the alpha particle, or a proton in this case, is a particle. It has a high energy transfer per unit mass. The first graph that I showed you, the DNA, the 2 strands, I showed you an electron, I showed you an alpha particle. The alpha particle does a lot of damage, concentrated damage. Electrons do not. One more picture, a source of alpha particles inside a detector that shows the tracks. You see they're all straight, and they all go the same distance. Let's leave it at that. All straight, all the same distance. Here's another picture of what alpha particles do. This is a detector that I make in my own lab. It shows that at the end of their path, the alpha particles cause more damage. So we use them in radiotherapy when we want to do a lot of damage at a specific depth. That clear? Alpha particles, they go straight, they stop after a certain distance. At the end of their path, they do more damage. Electrons are light, so they zigzag. That's the difference. Heavy charged particles go straight, electrons zigzag. I see you're getting tired. I'm sorry. It's a lot of material. I try to go slowly, but I realize it's a lot of material. So once again, heavy particles straight, electrons zigzag. This would be an electron. Here's a comparison between an electron track and an alpha particle track. See the alpha particle very short, the electron zigzags, and sometimes it creates these additional tracks. They're called delta rays. In fact, sometimes the electrons even produce X-rays when they slow down. Let's go back to our concept. Electrons zigzag, maybe they break one of the DNA strands, but they will not break the other one. Between the interactions, there's typically 10 nanometers, whereas the separation between the DNA strands is 2 nanometers. So if they damage one side, they will not damage the other, and that is good. The problem is when you damage both sides, and then the DNA may have two segments that separate. Here's again an autoradiograph showing that electrons have a zigzagging path. In this case, it's a piece of rat brain, again in contact with a radiographic film. And this is a Monte Carlo simulation of those electrons. Let me skip this. The range of electrons in air depends on the in water depends on the energy. So the higher the energy of the electrons, the longer the distance that they travel. Final one. Then we take another break. Photons. We said that we have two types of photons. Coming from nuclei, we call them gamma rays. Coming from atoms, we call them X-rays. They can come from atoms in two ways. Either they knock out an electron, and then they rearrange their distribution and some X-rays come out, or they can move near a nucleus. They are negative, the nucleus is positive, so they get deflected, deviated from their path, and an X-ray is emitted. So what do these interactions do? And that's when we take the break. Photons do cause different types of effects. When their energy is very low, they cause molecules to rotate or undergoing torsion. This is how you heat up your food in the microwave oven. When you use waves whose frequency corresponds to the frequency of agitation of water molecules, you'll cause the water in your food to agitate more and to warm up. The beauty of it is that it's only the water molecules that move, that get accelerated. So your plate, your dish, if it's made of ceramic or glass, it will not get warm. Okay? That's why you can put a dish in the microwave oven. You take it out, your food is hot, the dish is not. Let's increase the energy of the photons. We now hit infrared and then visible, because remember, visible is between infrared and ultraviolet. Ultraviolet is the first region where radiation can cause ionization, the effects that we just mentioned. That is why when you go to the beach or to the desert, you gentlemen up there, and expose yourselves to the sun, you have to wear sunscreen that blocks ultraviolet radiation, because ultraviolet radiation can cause damage to the skin. It's not like the alpha particles that stop. Ultraviolet penetrates and it can cause damage to the skin. So you need to block it with sunscreen. When the energy is even higher, and that is going to be our next topic, it starts causing ionization of different kinds. So let's take another break. I believe you need it. Please come back within, well, if we can do 10 minutes, but let it be exactly 10 minutes. Otherwise, I will not be able to cover all the material.
Sir, I have a small question.
Please.
Now, what I understand, I heard something, but I'm not sure about it. They say alpha, this we can cover it and cannot filtrate, but it's more dangerous than
Yes.
the gamma.
More than gammas. Neutrons, I haven't described yet. Neutrons can do damage, significant damage.
But gamma and beta, alpha is the move in vocal.
Yes, between gammas and betas and alphas.
The wave and the waves. It's it.
So
Too much.
photons are waves, gammas are particles, just like betas. But compared to betas, they're bigger. They have more charge. That's why they do more damage. Neutrons are not charged, but they hit nuclei, and those nuclei are charged. That's why neutrons are dangerous. Are you from the Emirates? Are you from Abu Dhabi?
Yeah.
So you have nuclear power plants that were built by Koreans there.
Yes.
I've been collaborating with the yes, the Abu Dhabi Civil Defense Authority, and in fact, I value that collaboration a lot. And something that I have been suggesting for a while is that you equip yourselves with devices that can measure the radiation that might come from the power plant. I'm sure you've done it in the meantime.
We have a DMC.
You have it. You had your, okay. Because among the radiations that are produced by reactors are neutrons. So one has to make sure that the shielding is appropriate. I'm sure it is. I'm sure it is. But to my knowledge, my understanding is that the reactor is operated by Koreans.
Yes.
Exactly.
That's
So,
what I have, yeah.
so you need to monitor what happens, obviously.
Okay.
That is the one thing you can and must do to make sure that your own health is protected adequately. As I said, I'm sure that everything is in order. I'm sure they do everything right. They know what they're doing.
Yeah.
But it's good for you to supervise.
I will, shall. Hopefully, one day. All right, thank you, sir.
Of course. Tutto a posto. Mi sento molto in colpa facendo le 8 ore, se sono ammazzata a sti porelli. Io provo a far pause, a rallentare. È dura.
Professore, prima mi sono nemmeno presentato. Mi chiamo Emiliano, molto
Emiliano, piacere. Io sono Francesco.
Sì, mio fratello la saluta tanto.
Ah, ringrazio.
Scrittora.
Ringrazio di cambio.
Saluta tanto.
Ringrazio.
Vabbè, allora glielo dico, se ne sarà molto felice.
Stasera mi devo fare 4 ore d'auto per tornare a Pisa e domani mattina devo insegnare là. Non oso pensare a condizioni in cui sarò.
Beh. Già quando comunque devi guidare tante ore arrivi distrutto.
Infatti. Esattamente.
Bella lezione.
Ma sono tante cose, ho paura di...
No, però è molto chiaro. Bella lezione.
Grazie.
Prego.
Grazie.
Mi è piaciuta molto.
A me piace insegnare
Sì,
e
io c'ho una professoressa che dice quando diventa la lezione, cioè, il professore spiega quello che sa. Cioè, dopodiché, se siete fortunati, l'argomento coincide con l'esame. Se vi spiega un'altra cosa.
questo è un altro punto molto importante.
Sì.
Io che da studente ho visto professori che abusavano degli studenti in modi più assurdi, cerco di attenermi esattamente alla regola che mi aspetto solo quello che vi ho dato. Cioè, e l'altra cosa che cerco di fare è raccontarvi cose che ho fatto piuttosto che cose che ho letto, che tutti possono leggere. Certo. Cerco di darvi quello che dovessi avere domande o commenti, spero di saper commentare. Qui spero di saper rispondere. Questo è.
Però no, pensavo,
Ragazzi,
davvero, ci siamo visti
infatti io mi ragazzi, io sono Francesco.
io Alessandro Rizzo.
Alessandro, molto piacere. Certo che ci siamo incrociati. Ti ricordo, non pensare di no.
Possiamo dare...
Molto volentieri. Ah, io sono partito presentando per nome
No,
e dando del tuo a questo punto.
Grazie.
Con molto piacere, ci mancherebbe altro. Gradisco commenti, gradisco anche commenti critici, per cui fammene senza esitare, perché io sto cercando di arrivare a tutti.
La base, cioè, secondo me è ben tarato.
E non sapendo siete di estrazioni estremamente variegate. E quindi inevitabilmente c'è una fetta di voi che si annoia, una fetta di voi che addirittura lo trova intenso.
Io penso, cioè, ogni concetto, diciamo, c'ha tante vie d'accesso. È interessante vedere le differenti vie d'accesso a quel concetto. Quindi, no.
Io cerco di darvi quello che credo sia utile per i passi successivi. Quando arriveremo a parlare di come le riveliamo, di cosa ci interessa capire, eccetera.
Domani anch'io ho 2 ore di lezione. Fortuna, diciamo, prima lezione è stato affrontato tanto la
No,
base,
spero.
quindi
Lo voglio sperare.
ero un po' preoccupato
No.
sull'inizio, diciamo, di dare...
Io so cosa dovete fare, tu e gli altri, e quindi sto proprio cercando di dare,
male.
senza entrare nei dettagli che fornirete voi, sia chiaro, però
No, però le
di
cose
darvi
fondamentali, anch'io, diciamo,
di partenza.
partivo dalla carta dei radionuclidi, davo qualche indicazione su interazione nucleare forte, queste cose, però logicamente poi avevo incentrato più su...
E comunque tieni presente certe cose è bene ripeterle.
Sì,
Per
no,
cui
sicuramente
il fatto stesso di ripeterle significa sottolineare che sono importanti. Il fatto di ripetere un'altra persona, altro stile, altro tono di voce, può benissimo significare che tu arrivi a persone che non ho raggiunto io, perché magari ho un tono che
la
dopo un po'.
sovrapposizione.
Io penso che aiuti.
Sì.
Eh,
No, però cioè, nonostante vabbè, è abbastanza basilare la relazione,
è chiaro che
però
lo è.
comunque interessante,
Questo-
mantiene
questo
il
mi fa
livello.
Questo mi fa piacere. Speriamo di portare tutti a seguire quanto gli sto per raccontare dopo.
Sì. Dico di rientrare.
Sarebbe ottimo.
Ok,
Sarebbe ottimo, grazie. Ti sto sfinendo? Prego.
Ma solo quelli sono iniziati, stato fondamentale. Non è per parlare tecnica. La base, non vale che anche gli altri è il fondo valida quello che non si no, quello che non dire i soldi che danno vuoi da leggere che se io lo leggo no, certo. Sì. No, dicevo che il positore non funziona per la sbagliata e il positore non viene chiesto se non viene aspettato. Allora, certi modo di cui prodotto perché poi ci sono si fermano dalle vari livelli di situazione. Per questo intendere i rischi stati. Questi sono livelli che sono stati citati, però sono caratterizzati da livelli di qualificazione che poi escludono come l'asma in modo differente. Quindi hanno che si saranno da quelle parte, quindi se loro hanno ancora più che forse fermi un po', per così dire, allo stato citato del Belgio, e scelte e ma sono la tappella sul mezzo
Question as we wait for the others to come back in. I am traveling at a pace of about 35 slides per hour. And I have exactly 35 times 8. That's a lot of slides. Question is the pace okay? Am I going too fast? A little bit too fast? Do tell me. I can skip a few details. I've done it actually, but again, if you see me going too fast, signal, stop me, slow me down. Please do, okay? All right, let's restart slowly. So we've looked at how alpha particles interact. I'll repeat it. They go straight. They're heavy, they're charged. They knock out electrons from their orbitals. In fact, they pull them out. They cause ionization this way. And at the end of their range, their ability to cause ionization ramps up. They cause a lot of damage at the end of their range. Then we've seen electrons. Electrons zigzag. It's easy to understand why. Electrons interact with other electrons. They have the same mass. So they scatter, as it's called, one another. Now we're looking at what photons do. We mentioned the fact that photons are either generated through nuclear decays, we call them gammas, or through interactions, changes in the shells of an atom. Those are called X-rays. The way they interact is the same. It's independent of how they were generated. That's why there you see X or gamma rays. They have the same type of interactions. And in fact, let's start from something they may not do at all. Sometimes they don't interact. So here comes a photon that just travels through these atoms, between these atoms, and has no interaction. See, a photon like this is not like light. Visible light, when it goes through the glasses, not because they're a little bit dirty, but because they're a different material, light slows down. When visible light goes through glass, its speed is reduced by the so-called index or refraction. That's because light behaves like a wave when it goes through glass. And as a wave, it has different types of interactions. These photons, they behave like particles. They don't behave like waves. They only interact if they touch an electron. If they don't touch an electron, they keep on traveling. So help me out. If they don't interact with an electron, where are they? How do they feel? Do they feel the presence of material or not? They don't. So they travel at the speed of light in vacuum. For them, between the atoms, it's vacuum. That's why the photons that we treat as ionizing photons all travel at the same speed. Their speed doesn't change. It's the speed of light in vacuum.
So don't have the refraction index.
Yeah. Yeah. So they don't follow the laws of optics. You cannot concentrate them, you cannot magnify them. A lens doesn't do anything to them. Okay. They don't follow the law of optics at all. These are particles. And as such, they interact with particles. They have a particulate, as it's called, behavior. If they don't touch electrons, they just go through and nothing happens. In fact, radiography is based on the fact that some of the photons will go through the patient and will produce an image here. We need their ability to go through without interaction. Otherwise, we wouldn't be able to produce images. Okay? But some of them do interact. And here come the main forms of interaction. When they interact with one of the internal electrons, those are the electrons that are closer to the nucleus. So what do we think? Are they tightly bound or not? They're close to the nucleus. The electrons are negative, the nucleus is positive. What do you think? If they're close, will they feel a strong attraction or not? Of course they will. Absolutely. Good. I'm happy when you reply. So those electrons, they don't really want to leave their orbit. They don't want to leave their shell. When a photon hits them, the electron absorbs all the photon energy because they don't want to leave their orbit. So they take all the photon energy, they absorb it, and they jump out as so-called photoelectrons. That's the photoelectric effect. When they are instead in external orbits, or shells, as I prefer to call them, their binding energy, is much lower. The very outer ones, at the outside, typically have a binding energy of about 10 electron volts. Very little. I remind you, that's 1.6 in 10 to the minus 18 joule. Very, very low energy. So removing those electrons takes very little. And when a photon touches them, they jump away immediately. So the photon doesn't have a chance to transfer all of its energy. It only transfers part of it. So following that type of interaction, we have an electron and we have a scattered photon. That effect is called Compton effect. But Compton will also happen when a photon has a lot of energy compared to the binding energy. So if your photon is a high energy photon, it will do Compton also on the internal electrons. Because for that photon, those electrons will be almost free. You understand? So you'll get Compton in two situations. When the interaction is with an external electron, because those external electrons are loosely bound, or when a photon has a very high energy. then no matter how high the binding energy of the electron, it is low compared to the photon energy. Okay? So in radiotherapy, for example, where we use very high energy X-rays, the interactions in the patient are all quantum interactions. Well, not exactly. If a photon has a really, really high energy, it may do something else. It may do this. The photon disappears and 2 electrons appear. So before we were talking about positrons encountering electrons and producing photons. Whoa. Okay. Now and that was the disappearance of mass, annihilation of mass, and appearance of photons. Now we're looking at the opposite process. Now we're looking at a photon that has enough energy equal to the masses of 2 electrons, and the photon can convert into 2 electrons. Now, why 2 electrons? Why not just 1? What would be the problem? Conservation of charge. So the 2 electrons are a negatron and a positron. Now look at the graph. See where the photon converts into electrons? Where does that happen? Near nucleus. This means that matter, because these 2 guys are matter, the 2 electrons, matter only appears when you already have matter. It's a good thing. Think about if you're, I don't know if you're interested in driving a spaceship. Are you interested? You are? I'm not. Anyway, suppose you're driving a spaceship and all of a sudden a photon disappears and you get, matter in front of you. That would be a problem, right? Well, that doesn't happen because unless matter is already present, you will not have generational matter. So you can drive a spaceship if you want. You're not going to run that risk. But stay away from meteor showers but anyway. Is that clear? So when a photon has a high energy, high enough, more than 1 MeV, 1.022 in fact, then it may convert into 2 electrons, negatron, positron. It's called pair production. What is the difference between what charged radiations, betas and alphas, and neutral radiations, gammas, X, and neutrons? The difference between their interactions with matter. Charged particles, we said it, they stop after a certain distance. This distance is called range. The range of alpha particles is very short. The range of betas is longer. But neutral radiations, gammas or neutrons, are only attenuated. They're not entirely stopped. They have an exponential attenuation. So it's an exponential, just like the decay that we described before. Now, before when we had decay, we said we have a half-life, the time after which the activity is half. So we'll have something similar, but now it's not time, now it's space. So we have a so-called half-value layer. So for each photon energy, there is a thickness of whatever material you're looking at, there's a thickness that cuts the intensity of the photons in half. So if your goal is shielding photons, you make sure that the thickness of material that you use is sufficient to cut the intensity as much as you want. It will never be to 0. You will need an infinite thickness, but you can reduce it to very reasonable levels. Yep. Half value layer. So very quickly, let's look at a couple more details of these photon interactions. They're very important. You'll have more classes in the course of the week. You'll be hearing about photons. You'll be hearing about what they do. Let's always keep in mind how they interact. So this is the photoelectric effect. This is a photon that has 100 keV of energy, and it interacts with this material. As you can see, this material has a binding energy of the internal electrons. You can read it, 33 keV. Can you see it? That is the first shell. We call it K shell. You know the Dutch Airlines, KLM? Okay, that's the name of the shells, KLM. They start from K, the internal shells, and then you continue, LM. All right. So that is iodine, by the way. Iodine has a binding energy of the K shell that is 33 keV. The next one, as you can see, has a binding energy of 5 keV, and then 1, and then they keep on decreasing until the very external one. How much is the binding energy? I've only told you 10 times, like 10 electron volts. Yeah, 10 electron volts. Remember that. When I say things twice or even thrice, it means you may want to remember that. Yeah, that's what I tell my students. So they always take notes. Okay, he said it twice or 3 times. Better know this for the exam. Better know this for the exam. All right, so 33 binding energy of the K shell. Your photon arrives with 100, but it only spends 33 to remove the electron. So the photoelectron jumps out with 67 keV. So now you think that I lied to you because I told you that the photoelectron gets all the photon energy. I didn't mean it. I meant that the photon spends all of its energy, but the photoelectron only gets the difference between the photon energy and the binding energy. So let's look at what happens next. You've created a hole. You created a so-called vacancy. You removed an electron. So an electron from another orbital will jump down and fill that vacancy. Then an energy will be freed equal to the difference between the binding levels. That's 28 keV. So after this photoelectron, you get an X-ray of 28 keV. What does it do? It gets absorbed. And the process continues until that vacancy leaves the atom. So you actually get a shower of lower energy X-rays. What do? They all get absorbed. Why do they get absorbed? Because the photoelectric effect has a probability that depends on energy like this. It goes up with decreasing energy, the probability. So following the first absorption, you get the release of a lower energy X-ray. It gets absorbed. The whole process leads to the full absorption of the photon energy, of the primary photon energy. Now, suppose you're using a detector and you're trying to measure this energy deposition. The question is, are you going to see many little steps in energy deposition, or will you see something that looks like a single event where the entire 100 keV as it was, 100 keV is deposited? You'll see a single event because everything happens so quickly that no detector could follow those individual steps. Everything happens in perhaps tens of femtoseconds. That's very short, very, very short. So detectors would not be able to resolve that. Detectors will measure the overall energy deposition. We will get to that. So here you see 2 things. You see that the photoelectric effect is more probable when energies are lower, but sometimes something funny happens. Look at this. This is lead. Lead has a binding energy for the K shell, which is 88 keV. So if your photon has 100 keV, can it remove an electron from the K shell of lead? Yes, it can. If it has 87, will it be able to do that? No, it needs at least 88. So when the photon energy drops below 88 keV, you'll have photoelectric on the following shell, the L shell, and the process starts again. That's why you have this sort of saw-like shape. It looks like a saw, okay? You also see something else. There's a big difference between the photoelectric effect in water. Takes this line here at this energy. You see water gives you a lot less photoelectric than lead. That's because the photoelectric effect has a probability proportional to the atomic number to the third. So lead has an atomic number of 82. Water is not a single element. What is water? It's hydrogen and oxygen. What's the atomic number of hydrogen? 1. What's the atomic number of oxygen? That's the mass number. What's the atomic? 8. Oxygen is one of those light nuclei that have equal numbers of neutrons and protons. 8 and 8. Carbon? That's nitrogen. Carbon? 6 and 6. Carbon has to be present in a material for us to call it organic. Okay? So there's no organic material unless it also contains carbon. Carbon is very important. And by the way, carbon is not only carbon 12, which is 6 protons and 6 neutrons. There's also a stable carbon 13. How many protons will it have? 6. Because if it had a different number, it wouldn't be carbon. All right. So that's an isotope. 6 protons and 7 neutrons. Nitrogen. 7 and 7. Let's start from the beginning. So the first one is hydrogen. How many hydrogens do you know? 3. Wow, very good. So the first one is hydrogen 1, only 1 proton in the nucleus. The second one, hydrogen 2, what is it called? Deuterium. The third one? Tritium. So let's go back to the first one. What's the name of the first one? Ah, very good. Protium. So the proper name of, that's very good. The proper name of hydrogen 1 is protium. And now let's look at the name of the nuclei of these atoms. What's the nucleus of protium called? Yeah, it's easy. What about the nucleus of deuterium? Deuteron or deuton. And what about the nucleus of tritium? Let's go triton. You know, just like a salamander, but it's a triton. Okay. Tritium is radioactive. Okay. It emits, yeah, it's radioactive. The other 2 are stable. So they're stable isotopes. What's next after hydrogen? Helium. The most common is helium-4, but we also have a helium-3 that is stable. It's very important in neutron detection. What's next after helium? Lithium. Lithium is 3. You know, we call it lithium, but think about it. We could just call it Mr. 3. Because once we give the atomic number, it's fully identified. It's only for historical reasons that we give them a name. It's simpler, or a symbol. And the older ones typically have a symbol with 2 letters, other with 1. I mean, it's a bit messy, but it's only for convenience. We could just call them 1, 2, 3, 4, etc. So who is 4? Beryllium, which is the stable version of beryllium. Beryllium is 4 as atomic number. What is the mass number? 9, exactly. So 9, he knew it. 9. So let's think about it. It means that it has more neutrons than protons. Now, if it were beryllium 8, it would be equivalent to what? To 2 helium nuclei, which means alpha particles. Now, the helium nuclei are very special. They like the way they are. So if you try to put them together to create a new nucleus, they're not happy. They remain as separate nuclei. So beryllium 8 is unstable. Beryllium 8 decays into 2 particles, 2 alpha particles. But if you add an extra neutron, then it serves as a glue and keeps things together. Beryllium 9. What's next? Who's number 5? Mr. 5. Mr. 5 is boron. We know 2 isotopes of boron that are stable. Boron 10 and boron 11. Boron 10 is important because it reacts with neutrons. just like helium-4, by the way. So after boron, which is 5, we have 6, we talked about him. After 6, we have 7, we talked about him. Carbon, yes, and then nitrogen, then oxygen. Who's next? Just 2 more, and then we stop. 2 more. Fluorine. Yeah, fluorine is atomic number 9 and mass number 19, not 18. It also needs an extra neutron to stay together. All right, who's next? And then we stop. It's the same family, but it's not neon. Very good. Very good. Okay, I promise that we will stop. So let's go back to water. Water, we said, was hydrogen and oxygen. And oxygen was 8, and hydrogen is 1. But the atomic number, as you can see, is the importance of atomic number for photoelectric is Z to the 3rd. So clearly, oxygen 8 to the 3rd is a lot more important than 1 to the 3rd. How much is 1 to the 3rd? It's 1. I don't know 8 to the 3rd. That's why I'm not asking you. Because, yeah, can somebody tell me how much is 8 to the 3rd with your phone or something? Yeah, 64 times 8. I don't think so. I think it's a lot more. It's 64 times 8. Anyway, it's a lot. So that means that oxygen pulls a lot more. So there's a formula developed by Mr. Maynard. I like that. I like that. I like the more or less. See, I'm an engineer. It's like an atmosphere. It's more or less 1 kilo per square centimeter. Okay. So a formula was developed by the scientist Maynard for mixtures of elements, such as water. You do the math, it's almost Z to the 3rd, not exactly, but it's essentially Z to the 3rd. And at the end, you have a cubic root. Because, of course, you need a linear value Z. So Z to the 3rd under cubic root is Z to the 1st. If you use this formula, you'll see that water has an atomic number, an effective atomic number, as it's called, of 7.4. Lead was 82. So lead is more than 10 times higher, but it's to the 3rd that counts. So lead is really giving you a lot more photoelectric than water. Do you understand? Or did I go too fast? Here the point is, there's a lot more photoelectric in lead than in water. And the ratio between these two is roughly 10 to the 3rd. Because if you take the Z numbers of water, which is close to 8, and of lead, which is 80, the ratio is 10 to the 3rd is 1,000. Do you understand? So you get a lot more photoelectric in lead than in water because of the dependence on Z, the atomic number. All right. Here come a few more atomic numbers. I want to point out something. The atomic number of air and the atomic number of water are very close. What is air? Primarily these two. So nitrogen, that's why we did it. What was the atomic number of nitrogen? 7. Oxygen? 8. So the effective atomic number is between 7 and 8. It's a bit higher than that of water, 7.6, but it's very close. What does that mean? That if you take air and you expose it to photons, to gamma rays, to X-rays, you have the same type of interactions as in water. And why do we care about water? What is similar to water? It's written there. The muscles, the soft tissues of our body. And we are interested in what happens to our soft tissues. Why? Because cancer unfortunately develops in soft tissues. Then it may spread also to bones, but typically it starts in soft tissue. So The energy deposited in soft tissue is the same as it is deposited in water. And if we have a detector that is made of air, it's the same thing. It's the same type of interactions. And why are we interested in air? Because we can put air in a container and we can look at the ionization. We can measure the charge that is produced. That's why detectors filled with air, aside from the density effects, they have the same type of interactions as water and soft tissue. See, now we're starting to put things together. All the concepts we've introduced, yeah? And in fact, I'll show you as the first series of detectors that are so-called ion chambers, volumes containing gas. How much is the weight of a liter of water? How much is the weight of 1 liter of air? 1 gram, exactly. It's 1,000 times lower. That means that the interactions you have in a liter of air are 1,000 times less than the interactions you have in a liter of water or muscle. But it's only a density effect. The type of interactions is the same. That clear? So that's interesting. It means that we can make a dosimeter, something that measures dose, energy deposited, by using air, which is readily available, isn't it? Okay. All right, so that was photoelectric. Then Compton. Compton, we said, is when the photon is not fully absorbed, so we get a scattered electron, a Compton electron, and a scattered photon, a Compton photon. This effect is very important because when we do procedures on a person, on a patient, the patient becomes a source of X-rays. The person scatters X-rays. That's why in most cases, the radiologist sits or stands behind a shield. For example, glass. What do we put in the glass to make it a good shield? Lead, because of the high atomic number. Unfortunately, lead melts into glass easily. In fact, if you put lead in glass, it's easier to machine it. So you can do all the cuts that you want and you polish it as much as you want. It also helps, but it makes it a very good shield. So this is a leaded glass. Sometimes we have procedures where the radiologist must stand by the patient. Do you know what I'm talking about? Yes, for example, angioplasty. They're called interventional radiology procedures, where the radiologist stands by the patient, inserts the catheter goes to where you have, or I hope you don't, where people may have a problem in their vessels, a stenosis, that is an occlusion, and then it gets opened up. Yep. Unfortunately, there's no alternative. The radiologist must stand by the patient. So he or she must wear shielding, aprons and goggles to protect the eyes. The eyes are very sensitive. I'll show you. I hope we get there. Pair production. We already mentioned it. Pair production, a photon disappears near a nucleus and 2 electrons come out, a negatron and a positron. Why is this a mistake? Beta minus and beta plus. I took it from a book, but it's a mistake. Why is it a mistake? Because this is not a radioactive decay. So these are not a beta plus and minus. These are a positron and a negatron. They don't get the name beta. They're not coming from a radioactive process. That clear? I know it's a detail, but
the nuclear doesn't change in this process.
yeah, it's not a decay.
It's only a catalyst.
It's not a nuclear decay process. It's no radioactivity. The name is wrong. That should be positron and negatron. And as you can see, the negatron zigzags and then it stops. The positron also zigzags and then stops. But when it stops, it emits an electron, a negative electron, and the 2 of them disappear. So the negative electron and the positron are antimatter for one another, just like the antineutrino and neutrino that I mentioned before, antimatter. There's also an antiproton, there's an anti-me, an anti-whatever, okay? So there's antimatter. I don't know if there's an anti-me, honestly. Is that clear? Antimatter. What meets matter disappears and releases energy. The summary is here. We have photoelectric depends on energy as 1e to the third, or z to the third. Quantum doesn't depend much on energy, doesn't depend on z. Again, there's no time to elaborate more. Pair production starts in water and tissue at very high energies. That's why you can neglect it in radiotherapy. It's very little in radiotherapy. It's possible, but in radiotherapy, you mainly have quantum, almost only quantum. There's something else that I haven't mentioned. This is called simple scatter. The reason I have not mentioned it is that it doesn't cause ionization. It doesn't cause ionization, so for us, it's irrelevant because it doesn't do biological damage. Is that clear? Simple scatter means that the photon changes direction, but essentially doesn't change energy, essentially. But most of all, it doesn't cause ionization, so not relevant to us. This is a very important graph, one that you should know how to read. This is the graph that tells you what happens where. So this is photon energy, and this is the atomic number of your material. It tells you as a function of photon energy if you have mainly photoelectric, mainly quantum, or mainly pair production. Let me draw a few lines. This vertical line is the one for iodine 131. Technetium 199 metastable has an energy of 140 keV. Here's iodine 364 keV, and this is annihilation photons 511. These are important energies in nuclear medicine. Let's draw some horizontal lines now, if I manage. Oh, here it comes. This is a line at 50. It's a detector called sodium iodide. We will see that. Another detector. Sorry, I wanted to draw another line first. It's not coming out. Very strange. Okay, I wanted to draw. Here it is. It's white. This line here is the one for soft tissue. I don't know why it came out white. I copied the slide and it changed the color. This line is at 7.5. That is soft tissue. It's muscle. You see that in soft tissue, we quickly have dominance of quantum. In bone, quantum starts prevailing at a higher energy, 60 keV versus 30 keV. Why do I mention these two energies? 30 keV for soft tissue, 60 for bone. Because when we do radiography, we're in the middle. So in soft tissue, we have quantum. In bone, we have photoelectric. That's why you see the bones white. They absorb the X-rays through photoelectric, whereas muscles allow rays to go through. It looks black, okay? So I just want you to be able to put all these things together because everything is connected. Summary. This is, again, showing you what heavy ions do. They stop. What electrons do, betas and electrons, they stop. What neutrons and gammas do, they are attenuated exponentially. Now, I wasn't sure that it would run on this computer because I use a Macintosh, so I cannot show you the animations, but I will show you these results of calculations of how far photons go in water. This is a Monte Carlo simulation of 10 keV photons, very, very low energy, in 10 centimeters of water. So these are 10 centimeters. What do the photons do? They all stop. Just a few are backscattered. They all stop. They stop within a centimeter or so. And they stop via photoelectric absorptions. Because remember, photoelectric dominates in soft tissue up to 30 keV. So that's photoelectric. Let's move on to 30 keV. See how quickly things change. Now photons are sometimes absorbed, they stop. Sometimes they even go through 10 centimeters of water. And we have some scatter already. You see they're deflected. It's scattered. Let's go up to 100 keV. Look at the amount of scatter that we're getting now. And look at the number of photons that also go through. Let's go up again. 300. Now photons really go through a lot. So we have quantum and we have transmission. You see these little red dots? These are the electrons depositing energy. let's go to an even higher energy, 1 MeV. Now those red dots have become little segments because the electrons travel a longer distance. 1 MeV. Does anybody remember the energy where we have pair production? One 0.022 or 1022 kV. So do we have pair production here? No, we're below the threshold. It's a threshold effect. But let's go to 10 MeV. The pair of red lines are pair production. Now we do see it. You see it up here. This is a pair. This is pair production. Those are two electrons, positron and negatron. You see them? So that's what happens up there. This is just to show you what happens for different photon energies. Okay. Radiation hazards and concerns. Let's get into now we have the basics. Now you have no excuse. Now you have to follow what we're talking about next. So this is your chance. Do you have any questions? Because now we're going to use that stuff. I promise.
Simulation, the line, check.
The straight lines are the photons.
Yeah.
Yeah. Then they turn blue when you have Compton. They turn red when you have an electron.
It's trajectory and the distance.
Exactly. Exactly. And some of those black lines go through the 10 centimeters transmission. Hazards and concerns. Why concerns? Well, you know that there are lots of sources around. They can be removed. They can be diverted. They can be misused. People can cause accidents in principle in nuclear power plants and cause a release of radiation or radioactivity. We may have improvised nuclear weapons, not easy, but possible. We may have what's called dirty bomb, a radiological dispersal device, or a radiological emission device. What's the difference? A dispersal device is where you put a radioactive source next to an explosive, you detonate the explosive, you release radioactivity in the atmosphere, in the environment. That doesn't necessarily kill people. That doesn't necessarily cause significant biological effects, but it prevents access to certain areas, to certain facilities. In the States, they're terrified at the idea that somebody may detonate a dirty bomb on Wall Street and paralyze the financial center. So many of the consequences may be not destruction, not killing, but disruption that is interfering with normal operations. Then there's the possibility of radiological emission device. You take a source, a big source, and you stick it under a chair, maybe on a train or a bus. A person sits on it for 5 hours, that person is not going to have children. At least, you understand. The dose may be so high that it damages the reproductive system of the person. You follow me? That is an actual biological type of consequence. And of course, a nuclear device, meaning an improvised nuclear device, that is a mass destruction device, lots of casualties. So the stress is on the psychological impacts. Radiation is considered the quintessential source of fear. It causes fear. And the reason is quite simple, as everybody here knows, you do not smell it, you do not hear it, you do not touch it. Our senses do not allow us to perceive the presence of radiation. And think about it, when a person undergoes radiation therapy, that person goes, receives 2 gray typically each time, feels nothing, absolutely nothing. So we don't really feel it unless it's a massive exposure. Not only do we not sense its presence, we do not sense the effects, not immediately. Fear, panic, what do they come from? Well, they come from the rush to leave an area where there's been an event. So injuries may come from that. Think of people getting scared when they run out of a stadium because something happens and they stumble to one another and they hurt one another. Same thing is a possibility. They may flood the hospitals, overwhelm the medical responses. You will have, in case of a similar event, a lot of people who are very worried, but nothing happened to them. And yet you have to deal with them. You have to talk to them. You have to examine them. You have to reassure them. These are the so-called worried well. Panic spreads, panic contaminates. It spreads everywhere. And the other thing that may be exploited is fake news. So the possibility that there was no real bomb, but the rumor is spread that there was a hoax, and that will cause the fear. All these may cause a lot of damage at the economic level. It can also cause long-term contamination. So cleaning up may be a real problem. I'll show you about an accident that took place in Brazil. It was a major disaster. The other thing is, because you do not detect it unless you have detectors, you never know if there's something going on. So it's a really perfect device. High effective resource ratio. Quintessential source of fear. Look at this. These are, I leave the table. I will not comment on the lines. You can read them. Here you see the consequences that different levels of exposures. I'll tell you what a gray is. It's a joule per kilogram. It's a measure of dose energy deposited by radiation. Look at the level of damage or consequences. Not only health, but really psychosocial, political, economic, environmental. When Chernobyl took place, people panicked, even very far away. They panicked in Washington State, which is on the west coast of the United States, very far from Chernobyl. They panicked and they ran to get potassium iodide, tablets. An accident at a power plant releases, among other isotopes, iodine 131. Our thyroid needs iodine for its normal operation. So when iodine falls out onto the ground, it goes into vegetables, it goes into dairy products, milk. If we ingest it, it will target the thyroid. It can potentially cause thyroid cancer. One way to prevent that is to saturate our thyroids with stable iodine. So you take stable potassium iodide, your thyroid takes as much as it can. At that point, if you get radioactive iodine, it doesn't go into the thyroid. The thyroid is already saturated. So people ran to get tablets and they went crazy. Washington State, very far from Chernobyl. They even stopped drinking milk, eating vegetables. Another case that really caught the attention of the world, an accident that happened in the state of Goiás, city of Goiânia in Brazil. A cesium source, radiotherapy source, was stolen, opened up, and distributed in the environment. To make it worse, people painted themselves with this shiny powder that is cesium. Only 4 got very serious exposure and died, but 112,000 people flooded the hospitals. Think about it, 112,000 people. Even in a big city, getting 112,000 people altogether to the hospitals, it's impossible to manage. You've been to Brazil? It's a beautiful place. I have a joint appointment there. I go all the time. It's hot. It's hot. So people were there waiting in line in front of the hospital, fainting from the heat, fainting from the panic, and vomiting from the fear. These are all the same symptoms you get from an acute radiation exposure. So potentially they had been irradiated. You couldn't tell. They were vomiting from the fear. Nausea is one of the symptoms of acute radiation exposure. Imagine dealing with this. And imagine the consequences of the ignorance. So after the accident, People didn't want to do business with the city of Goiânia. They didn't want to buy anything coming from there. They didn't want people from that city to move to their cities. They had to do a massive, massive decontamination and cleanup effort. I forget the number of tons of ground, of soil that was removed and stored until it decayed enough. So what is the story? This is the path that we have to avoid. You have to understand it. You have to avoid it. You have to avoid a situation where fear is triggered by inadequate, inaccurate, insufficient information. It spreads, it creates myths, wrong impressions, and at that point, it causes all those reactions. You need to know facts. You need to share facts. Ideally, you want to create this. This is called the ladder of public involvement or public knowledge. And what it means is that if you increase the knowledge of people, they can make the right decisions and they can help make the right decisions. You start from persuading them. That's the basic level. It's not a good thing to do. It means that they don't really fully understand, but they trust you. They accept what you say. You're persuading them. Much better is when you educate them. That is, you share information, they become owners of that information. They can use it themselves. They start providing feedback. They start feeling engaged, involved. You want to increase the engagement. At that point, you may start consulting them. You ask them their opinion. In fact, you may invite them to join the decision-making process, the joint planning. At some point, you even give them responsibilities. You delegate authority. You understand these are all increasing levels of knowledge and use of the knowledge. And finally, they reach self-determination. They know what to do. This is exactly the opposite of what happened in Fukushima. So Fukushima, as you know, is the accident at Fukushima, consequence of the seaquake or tsunami, now we call it with the Japanese name. What happened is that the power plant lost connection to the outside. There was no power supplied, so it couldn't operate the pumps that keep the reactor at a reasonable temperature. A lot of things happened. The diesel engines that were supposed to operate those pumps were put underground. So the wave of tsunami flooded the whole place. Information had been ignored. There were records of tsunami waves higher than 10 meters, but the barrier was just 10 meters. 10 meters is high, but there was evidence that it had been exceeded in history. Anyway, the point is, the diesels were out of service because they got flooded. They were underground, very poor design. The batteries ran out. At some point, there was no more cooling for the reactors. And without getting into the nuclear engineering issues, there are reactions that happen when some materials exceed certain temperatures. They get oxidized, they release oxygen and hydrogen. And that's what happened there. There was a hydrogen explosion. It was not a nuclear explosion. It was a hydrogen explosion. The Japanese get trained. They get trained on how to react to an earthquake daily basis, how to react to an epidemic, pandemic, how to react to a chemical attack. They had a sarin attack on the subway. So they know what to do in those cases. But Japan could only install nuclear power plants in Japan by declaring that was zero risk associated with nuclear power production. As a consequence, they never trained people for a possible accident because the accident was impossible. So people didn't know what to do. People had no clue what to do. They were as far as possible from this. They were down here. And in fact, they were persuaded by propaganda about the consequences and the risks because they had to access through their cell phones sources of information. There was a lot of misinformation and panic spread at that point. You understand? This is what we need to avoid. We need to avoid manipulation, which is persuasion in a way. Anyway, sorry about the detour. So what is it that can happen I do these few more slides, and then if you wish, we take it's 12. When do you want to have lunch? 1 o'clock? Should I continue straight until 1? Yeah, see, the topics are lighter now. Say foolish things, I make a fool of myself, I keep you, I hope, awake. Yeah, all right. So, no, but this is serious. What is it that radiation can do? It can cause external exposure or contamination. External exposure, radiation goes through our body or parts of it and causes ionization, potentially biological consequences. Contamination is when radioactive materials either deposit on our skin. If we have wounds, they enter through the wounds, or we incorporate them, we inhale them, we ingest them, eat them. So internal contamination, it goes inside. External contamination on our skin. External exposure goes through us. 3 different things. External exposure, you have a source, it emits gamma rays, for example, we're exposed. You remove the source, end of the story. But if the source also emits radioactive particles, those particles will deposit on our skin, we will potentially inhale them, potentially they will go to our lungs. What's on our skin, in principle, we can get rid of by showering the body, by using very mild, this is important, using very mild detergents, very soft sponges, not hard brushes, not aggressive detergents, because you will open paths through the skin, and then what is on the skin will go inside, much worse. Okay? If you strip a person who's been contaminated of the clothing, you're removing 90% of the contamination, typically, order of magnitude. You guys who have hair, I don't have that problem. Cut the hair. That's another very powerful way of getting rid of the contamination. Okay, so these are the things. Contamination, exposure. Yeah. And what are the consequences? What are the effects? I will cover this very quickly. You will have classes, dedicated classes. It's a topic I do work on. It's a topic I do research on. I've been trained on it. I have worked, I started my career in the United States. I was in a medical school, first in therapeutic radiology and then diagnostic radiology. So we had to do a lot of this because it's part of the planning of treatments, understanding the radiation effects. But again, you will hear about this from other excellent teachers. So what is radiation biology? As it says there, it deals with the consequences of interaction between radiation and tissues. Starts from the chemistry, the chemical basis. Don't forget something very important. With very few exceptions, we don't know if cancer was caused by radiation or by a chemical agent, because the type of damage is the same. It is the disruption of the DNA strands, of the chemicals, of the bases of the DNA strands. And you cannot trace it necessarily to radiation. Of course, if somebody is exposed to fallout and you see thyroid cancer, well, clearly. If someone develops mesothelioma and was exposed to asbestos, which is not radiation, then it's quite likely that that caused it. But with very few exceptions, we don't know if cancer came from radiation or other sources, chemical. It starts from alterations of DNA. We'll look at how cells respond in different phases of their cycle. We'll see how organs respond, but very, very quickly, and talk about the risks. This is an important graph. It shows the so-called paradigm of radiation injury. So you have ionizing radiation, it interacts. And remember, we said we can have ionization or excitation. 2 things. Excitation essentially means electrons that jump and then go back. At most, they heat the material. It gets a little warm. hard to measure. I'll show you. Very hard to measure. You need a dose that would kill 4,000 people to increase the temperature of our body by 1 Celsius. The dose that kills a person, 4 gray, increases our body temperature by 1,000th of a Celsius, which is almost impossible to measure. So that dose would kill you and you would feel nothing. You would feel nothing. There would be no effect that you can perceive. But again, that's a dose that kills. Doses that we encounter daily or in diagnostics, we don't feel anything at all. Ionizations may happen. If ionizations occur, they may do damage to the DNA. In the vast majority of the cases, that's immediately repaired through chemical repair. We're designed to do that. But even if there is damage to the DNA, we have enzymes that kick in and fix pretty much all of the damage. But yes, there can be cases in which consequences occur. Sometimes the cells are damaged to the point that they stop reproducing. So you have cell death. If many cells die to the point that an organ doesn't function anymore, then okay, you have a consequence, a serious consequence. You may even have death as a consequence of that. If the number of cells that is damaged is very large. You may have effects that happen quickly, soon. It's called radiation sickness. Acute radiation syndrome. You may have late effects from large numbers of cells that are damaged. One of them, exposure to the lens of the eye. The lens of our eye, the crystalline, is very sensitive to radiation. A long time ago, it was underestimated how sensitive our eyes are. I'll show you. Something like 1/3 of a gray can cause cataracts. So we need to protect our eyes. Now, we're not talking about X-rays or gamma rays. We're talking about ultraviolet radiation in that case. But ultraviolet radiation contains, I showed you before, an ionizing component. So it can do that kind of damage. There can be late effects. There can be developmental effects that are transmitted to the fetus, to the offspring. Or they can be mutations. And mutations can happen along the germline, so they're passed on to the progeny, or they can occur in the person that was exposed. Those are called somatic effects. And in the worst case, we're looking at cancer, malignant cancer. Do we know the definition of malignant cancer? It's the one that spreads. It's the one that metastasizes. When it stays confined, it's much more manageable. It's not a good thing, but it's much more manageable. When it spreads, when it attacks other organs, that's what we call malignant. You remember before I told you that in the photoelectric effect, we don't see all the different energy depositions because they all happen within an incredibly short time frame in the order of 10 to the minus 15 seconds, femtoseconds. It's impossible to detect them. Unless you have the most incredible types of detectors, it's impossible. So that is the so-called physical stage of the interactions. The interactions are completed. Then again, you can read it yourselves. I want to move on. I'll give you this text, so no point in me reading it. There are phases that are called pre-chemical, chemical, and finally we have the biological stages. They start after 1 millisecond. You already see things altered at the biological level after 1 millisecond. That's because you may have cells that are at a very sensitive phase, which I'll describe in a second. Biochemical changes within seconds, minutes, already cells are affected in their division. And then within days, weeks, and years, you see these consequences, possible consequences. So we define somatic or heritable effects. Somatic in the irradiated individual, heritable transmitted in the offspring. Two more important definitions: deterministic effects, stochastic effects. So deterministic effects. They happen when a dose is received that exceeds a certain threshold. There are some effects that only happen, but they will happen, if a dose is exceeded. And the higher the dose, the worse the consequence. There's only one that doesn't get any worse if the dose exceeds a certain threshold. If we get 4 gray to the body, we die. Doesn't really get any worse than that. 4 gray to the body, to the whole body, will kill a person unless you do some medical treatment. Do you understand? But in the other cases, when the effects don't kill people, the higher the dose, the worse the consequence. Io andrei avanti fino all'1, mi hanno detto. Vai. Spengo il microfono. Qui abbiamo segreti, eh?
No, no.
Ah, lo so che
Con
con gli occhiali.
Sorry,
This is very
this is
important.
very important matter.
This is my lunch.
Yes, exactly.
Okay, what do I want?
Pollo, paniere, merendine.
Mi piace tutto. Caponata di manzana.
Ok,
Quella
con,
roba lì con... Ah,
con cosa vuoi? Con pollo, straccetti,
Questo straccetti.
pasta? Ma non mi ispiravano, sinceramente. Poi,
Vai, straccetti.
straccetti e caponata.
Grazie. Sei una tesora.
Qua fiscia, frizzante.
Sei una frizzante. Okay. So deterministic effects. They have a threshold. Some people are more sensitive, some people are less sensitive, but roughly it's a step. Not exactly a step, it's a sigmoid. But, you know, there's a clear dose at which they start happening. And normally they get worse when the dose is higher. The severity increases with the dose. We call them early when they're within days or so, erythema. So there was a time when dosimetry wasn't well developed, but radiobiology wasn't also well developed. So radiotherapy was carried out by irradiating until people became red. Yeah, you know, they had to stop at some point. They say, okay, you turn red, let's stop, come back tomorrow or in 2 days or whatever. Now, erythema, the transient erythema, the one that disappears, is maximum after about 1 day. It's like when you burn your skin. You burn your skin, it hurts. You pour boiling water. I'm not talking about really fire. You pour boiling water on your skin. You blister, you scream and shout, you curse, whatever. And after some time, it heals. So does transient erythema. It burns, makes you red, but then it goes away. But then there are the chronic, permanent, or late also effects. For example, cataracts, fibrosis. When lungs are treated, it's absolutely crucial to target the pathology of the lungs, because if you miss the target, fibrosis develops quite easily. Lungs are very sensitive. That is a deterministic effect. And again, I will not go through all of them. The other category, stochastic effects. It means random. It means they may or may not happen. These are the ones that have no threshold. These are the ones that even 10 electron volts, which we've repeated many times, can initiate. These are the ones that are due to changes in the DNA, mutations that may not be properly repaired and may lead years later to cancer. Important point. Cancer develops with significant delays. There are 2 categories of cancer. There are liquid tumors and solid tumors. Liquid tumors are the tumors of the blood, of the hematopoietic system. A significant exposure to radiation may cause cancer. Typically, it peaks 3-4 years after the exposure. Solid tumors, which is pretty much everything else, develops after decades, 20, 30 years, takes a long time. So the initial event produces that possibility for the sequela, but then you need additional circumstances that will cause it to spread, to really develop. Okay, let's see some of the deterministic effects. Let's finally introduce this concept that I've mentioned already. Are you still with me? Yeah? Even up there? All of you? All right. So let's introduce this concept of absorbed dose. Radiation may go through our body. It may transfer energy, which may not be necessarily absorbed. So we distinguish between energy that is transferred and energy that is absorbed. In fact, energy that is transferred takes another name. It's called karma. It means kinetic energy released in matter. But then we have absorption. Absorbed dose is the one that we will now refer to. It's a very simple definition. It's the energy deposit per unit mass of a material. Typically, we specify an organ, but we can use it for any material. In fact, in nuclear engineering, we talk about reactor dosimetry, and it means the dose to the components of a reactor. It's energy per unit mass, just like there. Here we refer to organs. So we do the integral of the dose over the mass of a certain tissue or organ. We divide by the mass or tissue. In the early days, in the United States, they still use it. There was the unit of rad, radiation absorbed dose. Now we use Gray in honor of Mr. Gray, one of the fathers and pioneers of radiation dosimetry, radiation protection. 1 Gray is equivalent to 1 joule per kilogram. Think about it, it's a little bit like the electron volt. We already had a unit, we had the joule, but we use the electron volt to stress that we are in a specific field, radiation physics, radiation effects. We don't need to say Gray, we could say joule per kilogram. We say meter per second, right? When we talk about a speed. So we could say joule per kilogram. No, we call it Gray because we want to stress the special field of application. Sometimes it's done. Okay, it's defined for all types of ionizing radiation in any medium, not necessarily living medium. We have other units. We've seen before for activity or radioactivity, the Curie, the Becquerel. Oh, notice something. When the name is written, spelled out, it takes a lowercase letter. In the symbol, it's a capital letter, uppercase. So when we write Gray, we write it with the lowercase g. When we write the symbol, it's a capital G, okay? And the same applies to the Curie, the Becquerel, the Röntgen, the Sievert, which we haven't introduced yet. Remember what I told you about the air being a good material to study the radiation effects? The very, very first effect that was studied was, in fact, ionization in air. It took the name exposure. It was measured in so-called Röntgen. Now we measure it differently with different units, but the quantity, in principle still exists. And just in case, the conversion from Röntgen to Gray is this one here. And if you're looking at photons, typically Gray and Sievert coincide. So you have this additional step. But please pay attention to the conditions that I said if you're looking at X-rays and photons. All right. These are the effects of a single whole body exposure. My God. Almost time to stop. Single whole body exposure. Okay. Down here. I've zoomed it, huh? How do I unzoom it? Who wants to get an extra mark, an extra grade in the final? Nobody? How do I zoom it, please? This is a Windows computer. I have no idea how. Zoom. You had a chance. Okay, I gave it to you. All right, so this is a very important graph. It's the so-called LD5030 that indicates the dose that is lethal to 50% of exposed individuals with death within 30 days. And as you can see, if humans are exposed to doses between 3 and 4 gray, and if nothing is done to them, no medical intervention, 50% of them will die within 30 days. It's clearly a deterministic effect. And this is the typical shape of the threshold, the sigmoid. This is true of all the deterministic effects, such as erythema, such as cataracts. Cataracts are a little borderline between deterministic and stochastics. I take it back. Erythema follows exactly a sigmoid behavior. On the right, you see the same quantity LD5030 for different animal systems. So you see they were clearly very similar to primates, were also quite similar to dogs. Other animals are more resistant to radiation. Typically, this is associated with a larger volume fraction of bone marrow. So when animals have more capability of producing blood, which fights the first effects of radiation, the ones that kill us first, they have a better resistance to radiation. And pay attention, those are animals that have increasingly rough lives, animals that risk being prey, attacked by predators, who do risk, injuries that severely damage their bone marrow. So they have extra bone marrow compared to us. We work with pretty much the minimum that keeps us alive. In fact, sometimes we don't even use all our bone marrow. Before, I think you said red marrow, you called it, right? Some of it, when we don't use it, turns yellow as it becomes more like adipose tissue. So the bone marrow changes based on our needs, but it's a slow process. If there's an injury that happens quickly, you will not see yellow converting to red very quickly, but it's there. This is the newt it's like a triton, it's like a salamander, it's an amphibian animal. Very, very high resistance to radiation. What's not listed there are the animals with the highest resistance to radiation. Does anybody know who they are? Yeah, cockroaches. So have you seen those movies, the science fiction movies, where a nuclear holocaust would only leave an Earth populated by flies and cockroaches? And it's true. It's true. Luckily, we wouldn't get to see it, but yeah. All right. About to stop. This is a very crowded slide, I know that, but I'll give it to you. What it shows, and I invite you to look at it yourselves, what it shows are, for different dose ranges, the interventions that are recommended, the treatments. You know the difference between treatment and therapy. Therapy cures, treatment addresses, possibly minimizes, mitigates. So these are treatments, which means they don't necessarily cure the problem, remove the problem. If doses are less than 1 gray, we're in the region where only very, very sensitive individuals will show some effects. Those effects are called prodromal, they're precursor. They will precede the real effects. In that case, what you want to do is reassure them. In particular, you'll have the worried well that we mentioned before, people who got very low doses, they need to be reassured. They need to be sent home rather than kept in the hospital and told, please, just stay there. We'll keep an eye on you. We'll do tests on you. We won't forget that you are in this situation, but you don't need a medical intervention. Don't stay here. You would just create problems for the others. You would hinder the treatment for those who need it. Typically at the level of You see at some point what's mentioned is nausea. Delay, here it is. Delay time prior to vomiting. It doesn't happen for those individuals. Below 1 gray, typically don't have nausea. If the dose is between 1 and 2 gray, there will be individuals, some 5% of them, that at 1 gray will start showing nausea. So now you have 20 people, one of them would have nausea from the radiation. You have 112,000 people that go to the hospital and many of them are panicking and vomiting. You think, oh, this is a high percentage. You think you're somewhere here, or at least it's possible, you understand? So if you base it on those symptoms, what you're going to do, you're forced to check those people one by one to see if they're contaminated, or maybe to even do some tests to see if they got exposed. They're different tests. Anyway, the one thing I want you to notice, the delay to nausea decreases with dose. If people start vomiting within an hour, less than an hour, it's really bad news. Very, very bad news. What can you do? At first, if the damage has happened, at first you want to help people fight infections. That is, our immune system is not able to cope with the infections effectively. And as it says there, so I will not ask you, as it says there, the first thing you can do is use antibiotics. That's the first line of defense. Now, our immune system, what is it? Now, it's not written there, so I'm asking you. How do we fight infections? Which part of our blood fights infections? Very good. So the leukocytes, the white blood cells, the leukocytes. Leukocytes live some month to 6 weeks. They don't reproduce. They're produced by the bone marrow, then they circulate, and about a month after, 1.5, they die. So if the damage is severe, you don't have much time before the immune system of the person is gone. So if the damage is greater than what's fought by antibiotics, you may think of the next line of defense, which is, just read it, transfusions. That's not enough, transplant. Now time is of the essence. Now you really have to act quickly before the person is completely without an immune system. So you have to do the preparations, you have to find a donor, you have to set up things to try and do it in a month or so, before all the pre-existing leukocytes, white blood cells, are useless. Yep. So that's the time frame. Again, other things are reported there. Skin injuries. Skin injuries are one of the deterministic effects that can, in principle, even happen in diagnostic procedures. Before we talked about interventional radiology, remember, interventional radiology, we said it's when the radiologist stands by the patient, inserts a catheter, performs angioplasty. Angioplasty means that you modify, you reshape a vessel, a blood vessel. There are two types of lesions. Stenosis, occlusion of the blood vessel, and aneurysms. Stenosis is when you have a deposit of plaque, calcified plaque, hard as a rock, have to break it, you have to reopen it, and then you have to do other things so that it doesn't reclose. Aneurysm is when the blood vessel loses its elasticity and a bubble develops. You don't want it to burst, otherwise you'll have a hemorrhage. If that happens in the brain, it's very bad news. It's a stroke. So sometimes the blood vessels of a patient are very complicated, and the radiologist has trouble going with the catheter to the region of interest. Then he or she may have to keep the beam that provides the images that guide the procedure to be on a specific spot for a long time. And if the dose exceeds a few gray, you will have erythema. If the dose reaches or exceeds 5 gray, erythema will be permanent. The effects will just remain. And again, I will not show you other pictures. It's one of those effects where the higher the dose, the worse the consequence. Another deterministic effect that does occur also in medicine when radiologists are not careful. Sometimes radiologists don't like to wear goggles because they feel that they look ugly with the goggles on. They look like this when they have the goggles on. So they don't like it, some of them. If they don't wear the goggles protecting their eyes, they may develop cataracts when they do repeated interventions. It's now estimated that 1/3 of a gray is the threshold. It's a very low dose. There was a time when it was considered to be too gray and people were somewhat relaxed. But exactly studying the interventional radiologists, we now know that about 1/3 of a gray can cause cataracts. It's a strange effect, the induction of cataracts. It's considered somewhat intermediate between stochastic and deterministic. There is a sort of a graduality in the probability that makes it a bit different from normal deterministic effects, but it's there. Last thing, studying these effects is something that used to be done on animal models. In the late 50s, early 1990s, there was a huge experiment in the United States involving 7 million mice. I repeat, 7 million mice. How do you say million? What's the prefix for million? Mega. So they called it the mega mouse, which is not a huge mouse. It was millions of mice, the mega mouse projects, something that would never be authorized nowadays. That was meant to study low radiation exposure effects. It was biased, by the way, so the whole thing was wasted. 7 million mice, totally wasted, because it was later found out that the guy in charge had a certain outcome in mind and forced data to support the ideas he had. So nowadays, fortunately, I should say, these experiments are no longer allowed. But one thing that can be done is using certain structures that are not considered animals, such as larvae. A model that is used extensively is larvae of zebra fish. So larvae of less than 5 days from fertilization are considered unable to feed themselves independently, and as such, they're not considered animals. This is something that my group, not me directly, but the biologists that I work with, investigates. And something interesting that you can see even in the short term is that there are some deterministic effects, such as, sorry, this is partly in Italian, such as the length of the fish after an exposure, a significant exposure. This is a 12 gray exposure in all cases. These are controls, these are mutants. And you can see in this case, there's clearly a shorter length of the animal. So there are ways to study these effects even without resorting to animal models. If the tests prove interesting enough, then you apply for the protocols. An ethics committee reviews the proposal. If it finds it justified, you can do work on these things. Okay, so now it's lunchtime, and then we restart from stochastic effects, which I'll do very quickly. You'll hear about these things again. When topics are treated more than once in this week, it's like when I repeat myself. It means they're very important. Take them seriously. Okay? All right. Non ti ho sentito più. Niente.
Noi mangiamo qui, no? Perché mi dicono che possono lasciare cose. Allora, ho fatto 118 di 275,
Però
ma alcune le posso settare. Sommato sempre abbastanza.
see you at 2. Thanks. Ce la faremo. Allora, vediamo tutta la truppa che siamo qui. Sì, sì, stiamo in pausa. Siamo tutto
Dopo un'esposizione dobbiamo perdere l'utilizzo di antibiotici per eliminare le infezioni perché il materiale si può perché il sistema immunitario viene alterato, i batteri viene alterato quindi che chiamo palletti oppure sono quelli turistici. Allora, no, bravo, più le cellule e strutture sono piccole, più alta è la dose necessaria per inattivare. Per cui inattivare batteri, virus, enzimi, lieviti, sai che le dosi non sono stesse. Quando per esempio si sterilizzano gli strumenti medici, dispositivi, vengono messi delle buste di plastica sigillate, ora sono possibilmente infettino, e poi vengono fatti passare sotto questi fasci di altissimo raggio di dosi. Dosi che si danno sono migliaia di quindi no, non è finisce. Grazie. È fatta no, in realtà abbiamo fatto assieme. Io ho imparato.
allora.
Diverso. Allora, non poi poteva essere
Grazie. Non mi iniziare, però la prossima volta dimmi è lì dentro. Ok? Perché se no mi ci abita.
Sì, ma
Uno si abita facilmente a essere coccolato. Non-
Pensando un po'.
Sì.
Now we are going to elections, yes. Okay, thank you, bye. Ciao. Noi pensiamo, stiamo arrivando molto bene.
Forse sono dei clienti, non si può sempre io li faccio vedere da un giorno.
Tu sai, tutti gli insegnamenti che fai non hanno il massimo delle valutazioni, quindi tu sai cosa perché se poi gli mancano i pezzi. Ma no, tu lo sai, appunto, perché poi magari non riescono ad agganciarsi.
Detto che certe cose interessano, per cui non si può fare per caso.
No, quello è fondamentale.
Magari da un punto di vista di
Non sono per questo.
cosa.
Ecco,
Tu
quindi,
non hai studiato.
esatto, ti li perdi subito altrimenti. No, no, no. Sono... No. Questo quindi devi ricordare le pitture.
E mangia di più.
No, no, mi devi portare io, ma fai avanza. No, adesso per voi, no. Oh. Oh, wow.
Le bubble. Ah. Ah. E comunque meglio di quello della mezza. Comunque meglio di quello della mezza, quando si medaglia.
Ah sì, sì.
Mamma mia.
Adesso ah? Mi devi dirci in borsa perché non so di cazzo.
Aspetta,
No, non si incrocia.
l'ultima. È l'ultimo. Ah. Oh, ciao.
No, pare Sanremo. No, sto meditando. Perché io ho scritto a Roman, perché stiamo a
Però, ma non mi devi.
no, io ho detto allora mi devi dire c'è l'aereo e il treno, ecco, l'aereo è la cosa preferita, perché sennò alle 5:40 a termine non perdi.
Sì,
È un grande problema e quindi fammi sapere se c'ho rimborsi. Se no,
no, sono attaccato.
ah no, ecco.
Guarda, vicino per passare tutto questo, perché se alle 7
Ma ci metto molto di minuto da passare con la macchina del Fiumicino per la
Ma soprattutto arrivate puntuale e fa prendere perché alle 9 c'è l'operato dove prendi, poi
io gliel'ho detto però a Matteo, fa, no, ma quello di fare, quindi non sarebbe neanche un grande problema che la possiamo gestire, ho capito, ma io che faccio? Metti che c'è crack, quindi non so molto che c'è uno sciopero, perché c'è anche uno sciopero in vista. 1, 22, 23, 1 questi giorni.
oh, se no puoi dire che manculo solo capire. Questo devo dire tutti quanti. Avvertite su ciò che fate, cioè nessuno vi dirà mai di fare una cosa piuttosto che un'altra, però se non siete in facoltà fisicamente scrivetelo sul gruppo e se siete fuori ma non state lavorando, state facendo altro, dite sta mezza giornata non sto lavorando, oggi non ce la faccio. Comunicate semplicemente la vostra presenza fisica e il vostro
stiamo qui alla unione della casa, perché
Qui il giorno prima dicevi sto a casa, il giorno prima dici guarda domani
oppure domani sto a casa ma non posso lavorare. Qualsiasi.
eh sì, perché noi contiamo che ci chiede e poi si chiede.
Sì, esatto.
Perché allora la regola base è che serve.
Io senza ricevere comunicazioni do per scontato che non c'è. Poi non è che devo pensare a lavorare da casa.
No, no, noi
Lavoro da casa.
no, infatti quando vieni per te risolvi,
Io anche poi però non lo sa, non è che
sì, guarda, domani lavoro a casa, oppure guarda, domani ho impegno.
domani mi impegno mezza giornata non lavoro, oppure tutto il giorno non lavoro, così uno sa che il giorno dopo, che so,
voi siete impegnati a fare altro, io vi faccio le attività che non posso fare con l'alba e non con voi. Ok. È solo una programmazione del lavoro, poi lo gestite in libertà, nessuno vi dirà sì e no. Ok? Tranne quando ci sono i master cerchiamo di stare qua, perché posso aprire la mano a tutti. Poi per il resto basta avvisare. Come sta andando?
Benissimo.
Ma secondo me benissimo.
Secondo me benissimo.
Quindi sta studio.
Ma tu non ti preoccupare, io te lo faccio. E non c'è stato modo perché sono...
L'ho vista lezione, vabbè, non mi presento perché sono stato studente l'anno scorso al Mander e
Vedi, sopravvivono ancora.
Questa mutazione.
certo, le radiazioni non hanno, almeno richiedono tempo.
Fino a...
Noi ci siamo considerati, sì. Anzi, per il futuro se non ho salutato, ma ero chiaro distratto.
Ma tu devi dire che lo studio non ho salutato, ma sono ordinario che non saluto i segnisti.
A te come sta andando? Che faccio
Lei ha consiglio di dire che lui ti proprio.
fa una brutta ressa.
A volte sì.
A volte sì.
Pensa,
A
dai.
volte sì.
A volte sì, insomma. Ma abituata.
Non puoi insegnare le scale larghe.
Se ancora devo spiegare, non dico che cazzate sono nessuno. Lei è la ragazza che ha detto di Gabriele invece non lo
Non stava qua.
Mai detto una
Pensa come
persona. Io che ho gentilmente sconfinato l'altro dopo un minuto.
Perché mi hai fatto venire il dubbio pure a me, perché non lo sapevo che era fidanzato
Mi ha fatto venire il dubbio pure a me.
Se magari possono
Pensate come mi tratterebbe se fosse in confidenza.
capito?
In teoria,
Poi siamo andati in macchina di Gabriele, effettivamente c'è stata una cosa, ci ha fatto perché lei lei ha abbassato lo specchietto e lui ci ha affacciato con un amico, allora è sicuro che piace, no? No, è una prova spiazzante.
Sulle spalle del culo. La settimana con più pressione della mia vita.
Non lo so.
come stai trattando? Non loro.
I
I
tuoi.
tuoi sono i anni.
Sì.
Solo in due non lo hanno passato, ma sono entrati in agitazione, non sono riusciti, sono stati 40 minuti anche al computer, gli ho chiesto 10 cose, non sono riusciti a fare niente, sono bloccati. La terza di giugno facciamo un'altra appello, invece di tornare la terza di giugno, rivedetevi un po' le cose, cercate di venire più tranquilli, è più un blocco nervoso che altro, insomma. La ragazza mi fa 3 ore di questo, ma adesso sulle spalle sta cosa mi funzionava non molto, perché così ma vedevo che funziona mo, no? È un po' come il tiro in allenamento. E fai 10 cose in allenamento, insegni in partita, perché
Però in partita c'è una missione, il fattore di pressione. Uno era il talento, non l'esprime.
Poi siete tu dietro, che sembri in cordo.
non so vedere che fanno.
Poverini.
Che funziona moltissimo. Come il beccatore di una fidata, il babuino una fidata.
È lo stress.
Sì, sì, no, traspirava, trasudava ormoni dal tipo.
Affidare.
Perché non stanno già?
Ma io ho leggere ingegnere, bisogno di seguire. Io posso pensare di cinque.
Quando, no, questo qua non si quando sono rimasto.
Quando prima? Non giorno venuto.
Magari uno.
Il ticket è da 5 euro, quindi equivalente di quello che ti prendi un doppio di trappa, lo prendi per 5 euro.
Cioè, così.
Tu 5 euro.
5 euro. Quindi qualsiasi cosa è buono.
Qualsiasi cosa che fai sotto i 5 euro, tra acqua e caramelle arriva a 5 euro, lo trovo sotto i 5 euro, perché non te la danno.
Allora,
Vabbè, dove andiamo?
vabbè, il caffè allora.
Ma poi bisogna fare, no, non fanno Parlato con Graziano Bonelli,
Mm.
fino a che uno studente ha già trovato il modo di collegare il
No, quindi, finché non pagano non glielo danno quello. E io che ti avevo detto stamattina che mi hai cazziato malamente, ora sarebbe il caso di chiedere,
no, ma fino a un mese e mezzo fa funzionava.
ma non fa tutto.
La connessione alla rete dell'Ateneo. Giravano degli account che usavamo tutti, no? Anche per la classe. Hanno disabilitato tutto, cioè devi avere il tuo singolo che ottieni con la posta elettronica che ti danno dopo che hai pagato almeno la prima rata di uno dei corsi che fai.
Paradossalmente l'unica persona che può accedere qua oggi è Mustafa.
Io posso immaginare. Invece, con l'università.
L'uomo sì, lo accedere
E no, sì, sì, no, guarda.
no, loro quelli nuovi.
Era quella proprio per far accedere loro sui norma, devono avere un indirizzo di posta elettronica students che viene generato dall'Ateneo solo a pagamento della prima rata, perché dice che c'era tanta gente che si iscriveva, non pagava la prima rata, però prendeva l'indirizzo, siccome ci sono collegati tutti i servizi anche per i paper, i libri.
A proposito, io avevo una richiesta di